Hello, everyone. Welcome to the September 2021 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. This episode is being brought to you from the Mindscape mobile podcasting unit, currently located in Boston, Massachusetts, rather than my usual home base of Los Angeles. With the pandemic clearing up a little bit, though obviously not entirely, travel is once again possible, and as some of you know, I'm spending the fall semester visiting the philosophy department at Harvard. Harvard was my graduate institution, but I was in the astronomy department. I did, though, take some philosophy courses because I was interested in philosophy at the time, so I got to sit on courses with John Rawls and Robert Nozick and other people, and some of you have heard this question, this anecdote before, but I got to know John Rawls. I chatted with him, very famous social, moral, political philosopher. And it turns out that he's really, really interested in physics and cosmology. So, he asked me because he was very fair, right? John Rawls' whole shtick was justice as fairness. And happily, this doesn't always happen, especially with moral philosophers, but John Rawls walked the walk as well as talking the talk. He was a scrupulously fair guy. I remember once walking through Harvard Yard and running into some of my friends who were in the philosophy class, and I was just auditing it, and they were taking it for real. So they had just gotten out of the final exam. And I said, so how was it? And they said, you know what? It was very fair. And a friend of mine who was with me immediately said, those must be your philosophy friends. I've never heard a physics person say that their final exam was fair. So anyway, yes, John Rawls was all about fairness. And so I asked him, even though I was just auditing the class, could I go to the section discussions, the small group discussions, which were led by him. And he said, the rule is if you're a graduate student, you can go to those sections. You're a graduate student, therefore you can go. Scrupulously fair. I was hoping to talk to him about philosophy and fairness and things like that, but once he heard that I was a cosmologist, it was all over. He's like, oh, you do that Alan Guth stuff. And so whenever we met, he would ask me questions about the Big Bang or things like that, different things in both mathematics and physics. I remember very well once in class, he was lecturing and he used the analogy, proving this is kind of like proving Stokes' theorem on an arbitrary differentiable manifold. Once you set up all the definitions, the actual steps are very, very simple. And I'm sure no one else in the class understood the power of that analogy, but I thought it was a very good one for me. So anyway, it's nice to be back as an official person in the philosophy department. Hopefully, I just started, so I haven't done anything yet, but part of my motivation here was to learn a little bit more about things like emergence and mathematics, philosophy of mathematics, different questions in logic and causation and things like that. But I will also confess that while I'm here, I'll be hanging out with my old friends, physics and astronomy, as well as friends at MIT and elsewhere. It's a real tremendous number of intellectual resources here around Boston, so I hope it'll be a lot of fun. And with that, we have a whole bunch of AMA questions. I think that the quality of questions is going up now that we don't answer every one of them. You remember the rules. I will answer a certain number of questions. It's nothing to do with the quality of the question you're asking. What the criterion is do I have something interesting to say about it? But people are definitely aiming their questions a little bit better now that I can't do every one. They're definitely trying to get in there. I do feel really bad for those who are not able to ask questions. Sorry about that. For those of you who are wondering how to ask questions, this is a benefit that you get from joining the Mindscape Patreon page. So if you support on Patreon, $1 per episode or more, that's up to you. You can ask questions for the AMAs. And then you also get ad-free versions of the podcasts. So that's a nice thing to do. Patreon.com/Sean M. Carroll. The biggest benefit, of course, is the feeling of happiness that you're supporting something that you enjoy. That's something that we can all get behind. And with that, lots of questions, so let's go. Michael Gordon says, during your AIP oral history interview in January, which for those of you who don't know, I did a long interview basically about my career in physics, etc., and that we posted as a bonus podcast episode back in January. Michael says, you expressed a wish to move toward a world where judgment was passed more directly on the merit of the ideas, in some opposition to the current environment of specialization and departmental segregation of ideas. Can you share more specifically why you believe a shift may be needed here, what you would like to see change, and if you know of any rigorous work being done in this area that quantifies how and what is lost in the process of specialization? So these are big, difficult questions, and I'm probably not an expert in them, in the sense that I'm in academia and I do work and I do interdisciplinary work. I'm familiar with some of the issues, but then I know very well familiarity is not enough to make one an expert. So take anything I say with a grain of salt. But look, the first thing to say is that the current system actually does work quite well. We get a lot of research done. We discover a lot of things about the universe. There are literally things like Science Week in Review. You can go see all the scientific advances that have just happened this week. Whereas 1,000 years ago, there weren't many scientific advances every week at all. The current academic/research system is pretty darn good at producing new, useful research. But that doesn't make it perfect. And I think that it's true that one of the ways in which it falls down is that it organizes itself, the whole academic research industrial complex, or whatever you want to call it, organizes itself in some way, like many institutions do, and that way is typically into fields or departments in a university. So you have physics, you have biology, you have chemistry, you have history, you have English, you have philosophy, and so forth. And these, in the modern university, these departments are largely self-sustaining. So the dean or the president or the provost will say, okay, you can have this many new faculty members over the next 5 years. But roughly speaking, the departments have 98% of the responsibility to hire the new faculty members and to choose what areas they want to hire in. There are some rare exceptions, but that's the usual rule. So as a result, it is kind of self-perpetuating. The physicists choose physicists, the biologists choose biologists. And so the people who are working in areas that are instantly recognizable as not only good, but also friendly to the notions of the discipline are easier sells for people who to hire than people who work at the boundaries, because different disciplines have very different standards, very different ideas of what problems are interesting, how much you should have published, and all this kind of stuff is different because you have a whole bunch of informal customs and rules that grow up, not just formal bits of knowledge. I have an upcoming interview you will hear soon with someone who feels very fervently that this is bad and it's caused us to not do as good research as we can. And I think that's right. I think that human beings are finite in their abilities to do things. You've heard that, whether it was in my interview with Carl Friston or Stephen Wolfram, we're computationally bounded. So we don't optimize things like a university to be perfect. We sort of have finite resources and we deal with them in a finite kind of way. It's easy and fairly effective to just organize departments and then be gone with it. But then you miss opportunities at the interfaces. So that does open the opportunity for places like the Santa Fe Institute to do cross-cutting interdisciplinary work. And of course, many administrators at universities give lip service to the importance of it. But at most universities, when they start putting their money where their mouths are, it's harder to actually do. So I actually don't know how to really solve it. I think that the current system, like I said, is pretty good. I don't want to overthrow it wholesale. So the least we can do is just remind our colleagues of the importance of looking a little bit beyond their disciplinary boxes. As long as it is faculty members in departments who hire new faculty members, the single best thing you can do to broaden the horizons of university departments is to broaden the horizons of individual faculty members. So say that interdisciplinary work is good, but also do good interdisciplinary work, right? If you can point to something and say, look at this result that we got because we were thinking in an interdisciplinary way and you weren't, that's what will really change people's minds. Charlie Schaefer says, from listening to you and reading your books, you suggest that the universe is ultimately understandable to the human mind. My question is, how do you speculate on that knowledge buildup, and how does that final attainment of that understanding play out, given the seemingly immense timescale of the universe? Do we have a continual buildup of knowledge? Is there always room for new discovery, or do we need to rebuild era after era? This is a great question. There's a lot of stuff going on here, so I will have to refrain myself from doing a whole solo podcast about this. But the point is that, it's not quite accurate to compare our knowledge of the universe to the size of the universe, right? Or the immense timescale of the universe. Because when we learn about the universe, we don't just learn a collection of facts. We're not just collecting every individual thing that happened in the history of the universe. That would be hopeless. We're collecting rules, we're collecting patterns, and it seems to be a feature of the universe that it obeys these patterns. And you can think of these patterns as compressions of all of the different ways, all the different events that happen in the universe. This is a Humean, following David Hume, a Humean view on what the laws of physics are. They are just very, very compact restatements of everything that happens in the universe. But again, it seems empirically from our experience that you need a small number of laws of physics and a small number of fundamental ingredients to account ultimately for everything that we see. So I'm not worried about the immense timescale or anything like that. It's quite the opposite. I am enormously shocked at how far we have gotten in understanding how the universe works right now. Now, there's a footnote here that is worth talking about. If you're interested, you can go back to the podcast I did with James Ladyman, who's a philosopher, who is one of the champions of what is called structural realism. Because you say at the end, Charlie, do we need to rebuild era after era? And there is sort of a school of thought in the philosophy of science that says exactly that, right? Some version of Thomas Kuhn's Structure of Scientific Revolutions picture says that we have a paradigm that we work within, and then ultimately the paradigm is overthrown in a revolution, and the new paradigm comes in and sees things in a completely different way. The structural realist, Ladyman and his friends, will say there is something that is preserved when we throw away the old picture and get the new one in, and it is the structure somehow. Even though the ontology might be different, the actual fundamental ingredients. So when you go from Newtonian physics to relativity, or from classical physics to quantum mechanics, your ontology changes in a profound way. But still, both general relativity and Newtonian physics give you more or less the same prediction for when the next lunar eclipse or solar eclipse is going to be, right? That kind of structure, those relationships between what you observe, is preserved over time. And so the hardcore structural realists will say that those structures, those relations, are all that exists. There's no real stuff that we're studying. We're just studying the relationship between, I guess, different observations. If you say you're studying the relationships of structures between things, that there need to be things in some sense, but I haven't completely understood this myself. So there are ontic structural realists who think that the structural realism point of view is really a statement about what exists. There's also epistemological or epistemic structural realists who think that this statement is just a statement of what we can know about the universe. So I think I'm closer to an epistemic structural realist. But the point is, even if we keep learning completely new vocabularies with which to describe the world, that doesn't mean we're starting again. That doesn't mean rebuilding. We're keeping something along the way. Okay, I'm going to group a bunch of questions together. We got a lot of questions about entropy and the arrow of time. Unsurprising, because we had that wonderful podcast with David Wallace. So let me just read a whole bunch of questions, and I'll do my best to say something interesting about them. Nate says, is there any interesting relationship between cosmological inflation or expansion and entropy? In particular, could expansion or inflation be changing the entropy capacity of the universe? Per Magnuson says, you've said many times that the presence of gravity made the entropy at the Big Bang low. Can you give an intuitive explanation for how gravity has this effect? Rainer Glüge says, is entropy not just an epiphenomenon of sufficiently complex systems, and hence not very fundamental? It may, for example, not be reasonable to speak about the entropy of the early universe if there were not enough degrees of freedom to apply an entropy concept. John Bergmeyer says, when you discuss the early universe having low entropy, how is that possible? I don't have an intuitive idea of what that would look like, since all the typical low entropy examples, unmelted ice cube, etc., still have a pretty high entropy and many different possible microstates. Nate Wadoops says, in your conversation with David Wallace, you said, "It truly blows my mind that even to this day, the reason why ice cubes melt and don't unmelt has something to do with what was going on 14 billion years ago at the Big Bang. Could you elaborate? I'm well aware that ice cubes do not unmelt, but I'm unaware of how that might stem from something that was going on 14 billion years ago." Okay, let's take these not quite in reverse order, but let's start with Nate Wadoops' question. I guess there's another Nate, just Nate without a last name, who has the first question. So, because this is the most basic one, what is this relationship of what is happening at the Big Bang to the fact that ice cubes melt but don't unmelt? It's not that ice cubes don't unmelt that is being explained here. The fact that ice cubes don't unmelt just comes from the fact that an unmelted ice cube is lower entropy, which means there are far fewer ways to arrange water molecules in a glass of water in the form of warm water plus ice cube than there are just everything is cool water or something like that, okay? So sitting by itself, it's not going to spontaneously go from a cool glass of water with no ice cube to a warm glass of water plus ice cube. So just to emphasize this, the numbers that we're talking about here are really, really big. You know, I think that if you haven't done these calculations yourself and people say, well, this is unlikely, this is going to come up later again when we talk about quantum mechanics. Over and over again, people say, well, this is unlikely. Physicists say the following thing is unlikely. And you can't help but think, well, so you're saying there's a chance. It's possible. If you're saying it's unlikely, it could be possible, right? Well, yeah, but really, really, really unlikely. If you converted all the atoms in the universe to ice cubes in glasses of water and waited much, much, much longer than the age of the universe, the chance that any one of those ice cubes would unmelt is very, very, very small, okay, over the whole history of the universe. So it's not something where occasionally it will happen. All right, having said all that, preliminary, what is being explained by the Big Bang is that there ever were unmelted ice cubes. That's the mystery. The mystery is not why you go from some configuration like an ice cube in a glass of water and it melts. The mystery is, given that there is a cool glass of water, why is it even plausible that there used to be a warm glass of water with an ice cube in it? Because that's a much lower entropy state. It's not the easiest way to get to a current configuration that looks like a cool glass of water. And that's what is explained by the Big Bang. The Big Bang itself was a state with very, very low entropy. In the coarse graining that we human beings use to understand the universe, the state of the degrees of freedom in the early universe was highly, highly special, highly, highly atypical, very, very low entropy. And it's the gradual increasing of the entropy since the Big Bang, which is very natural, right, that allows us to have ice cubes along the way and watch them melt. If it weren't for that boundary condition at the Big Bang, either, depending on what else you conditionalize on, either there just wouldn't be any ice cubes in the universe would be in equilibrium, which is just empty space and nothing going on, or whenever there was an ice cube, the future and the past of that ice cube would look the same, namely a glass of cool water without any ice cube in it. That's the easiest way to get an ice cube, is to just sort of take a glass of cool water and wait. It's very, very unlikely it will turn into an ice cube, but it's so many more possible starting points that you still win on the number of starting points there. Okay, so there, if you understood that, hopefully you did, but other people, John, for example, is asking, in what sense is the entropy of the early universe low? And Nate says, Per Magnuson says, what does gravity have to do with entropy being low at the Big Bang? So if you look at the state of the early universe and the Big Bang, it looks kind of high entropy. It looks like a thermal, black body, smooth, hot, dense state, right? And if you had a box of gas and it was glowing with thermal black body radiation, you would say that's high entropy. So it's not that gravity made the entropy of the Big Bang at the Big Bang low. It's that at the Big Bang, that early time, gravity was important. It's a big universe. There's a lot of matter in it. The universe is much bigger than the boxes of gas that you're used to doing in a laboratory experiment, okay? So in the box of gas in the laboratory, we just ignore gravity. We ignore the gravity pulling one gas molecule by another gas molecule. The Earth's gravity still matters, but the intramolecular gravity in the box doesn't matter at all. Whereas in the universe, it matters a lot. In particular, if you ask yourself, are there ways to arrange the stuff in the early universe such that the entropy would be much higher? The answer is clearly yes. And Roger Penrose, former Mindscape guest, recent Nobel Prize winner, was the one who really emphasized this, starting back in the 1970s, but he's emphasized it many times since then. A single black hole at the center of our galaxy, right? There's a black hole in the center of our galaxy, Sagittarius A, millions of times the mass of the sun. That has an entropy. We can calculate that entropy using Stephen Hawking's formula and Bekenstein and Hawking. And that single black hole has more entropy than the entire universe had at early times, okay? So clearly it's possible to take the stuff in the early universe and put it into a higher entropy state. Just putting it into a single black hole would be way, way, way higher entropy, okay? That's why gravity really, really matters. And that is why you can't say, to get to Nate's question, expansion or inflation increases the entropy capacity of the universe. This is a very intuitive thing. I know why you would think that. You're thinking, look, things are expanding, right? It's like taking a box of gas and making the box bigger. When you make a box of gas bigger, the maximum entropy does go up because now you have more room in the box, okay? But the point is, you're fixing the size of the box yourself. It's not a closed system, right? You are changing the size of the walls in the box as an external control, if you like. Whereas the universe is a closed system. The universe is just the universe. So you don't say, well, I'm going to fix the size of the universe or the density of stuff and then calculate the maximum entropy. I mean, you could do that, but who cares? It's a mistake. People do it all the time, but it's a mistake to think of that as the maximum entropy because the physical system that you're looking at is not a bunch of photons and atoms in a certain space-time. It's the photons and the atoms and the space-time itself. So you can ask, could it have been in a higher entropy state? And the answer is yes. Just put everything in a black hole, or for that matter, don't put everything in a black hole, but just expand the universe. That's a physical change in the system that is perfectly allowed and lets you have many, many more ways you can arrange the things, and therefore much, much higher entropy. Indeed, sometimes people say that the highest entropy state you can get is a black hole, but that's wrong. The highest entropy state you can get in a theory with gravity is just empty space. If you wait long enough, the universe will expand. Everything goes away. You'll be left with nothing but empty space, and you can show that is the highest entropy state. Aidan Chatwin-Davies and I, Aidan was a grad student at Caltech. He and I wrote a paper proving this result under certain assumptions, under a bunch of assumptions, but I think the assumptions are good. And it's actually fascinating, so let me explain. There is a theorem by Bob Wald, one of my old friends at the University of Chicago, brilliant general relativist. Bob showed that if you live in a universe with a cosmological constant, right, with vacuum energy pushing things apart, and you just wait, eventually either the universe recollapses or that vacuum energy pushes everything apart, and it sort of doesn't matter what the details were originally. It's much like when you make a black hole, all the hair oscillates away in gravitational waves, and you say black holes have no hair. So Bob Wald's theorem says it's a cosmic no-hair theorem. It says that it doesn't matter what you started with. Eventually you get to empty space with nothing but a cosmological constant. For years, this made me think of the second law of thermodynamics or of the process of equilibration, right? The ice cube melts. It doesn't matter whether you started with a glass of cool water or one ice cube or two ice cubes or whatever. Eventually, you get to a glass of cool water, right? They all go to the same place, just like the universe goes to the same place. So there's a equilibration, no-hair connection, and I thought we should try to make that rigorous. And so Aidan figured out a way to do it, and he and I wrote a paper showing that if you have a system in curved space-time with a maximum possible entropy, that system goes to empty space expanding exponentially, like it has a cosmological constant. And we didn't even use Einstein's equation or anything like that. So you can think of this evolution of the universe in the direction of emptiness as increasing entropy. So that's a proof that the highest entropy state you can be in is completely empty space. I think I've answered everyone's questions. Reiner Gluga said, oh, is entropy just an epiphenomenon and therefore maybe not applying to the early universe? You have to be careful what you mean by degrees of freedom, The early universe may have been dominated by inflation, by an inflaton field with no particles in it. But again, just like for the expanding universe, that is one particular physical configuration that could have been in a lot of other physical configurations, including a whole bunch of gas and dust, or a bunch of black holes, or empty space. All of these are other possible physical configurations of that early universe. It is not easy to write down a once-and-for-all formula for what the entropy is in such a situation, but we know it's very, very low. And we have pretty good formulas in certain special cases like black holes and like de Sitter space and things like that. So it is absolutely okay to apply entropy as a concept to the early universe. There are enough degrees of freedom there. Whew, okay. At this rate, this is going to be an 8-hour AMA, so I better speed up. Okay. Dan O'Neill says, I learned a lot from your podcast with David Wallace. Oh, yeah, it's another entropy question, but slightly different one. I learned a lot from your podcast with David Wallace on the arrow of time, but I'm still confused by how time's arrow relates to what we perceive to be the flow of time. I don't see how Boltzmann's probabilistic interpretation of the second law of thermodynamics explains why we feel that time is something that flows or that we move through. Well, yeah, that's perfectly legit. Didn't be confused about that. These are ongoing research problems. Let me explain the basic reason why we think that something like that is the right answer. According to the laws of physics, according to our best current understanding of the universe, time isn't something that flows. That's not a fundamental feature of time. Time's just a label on where you are in the universe, when you are, I should say, in the universe, where you are in space-time, if you like. And there's not even any difference between the physics of moving toward the future and the physics of moving toward the past at the fundamental level, at the level of the fundamental laws of physics. The difference between the past and the future comes exclusively because entropy is increasing, or more generally because the early universe was in a very, very special state, and from that state the universe is evolving, and that's what gives time its direction. That's where time's arrow comes from, okay? So if you believe that is the only place that time's arrow comes from, as I do, then any impression we have that time is flowing has to come from there. There's nowhere else for it to come from. And indeed, you can kind of see how that happens, because what you do is you connect the fact that entropy is increasing to other well-known features of the arrow of time, like you remember the past and not the future, your causal impact flows toward the future and not the past, etc. It's these aspects of time that give us the feeling that time flows. As human beings, and if you haven't listened to it, I encourage you to listen to the podcast episode with Janan Ismail, because we talked about exactly this. She's the world's expert on this. You're constantly carrying with you in your brain memory of what you were just doing, and also a prediction for what you're about to be doing next. I talked a little bit about this with David Purple also. So it's that comparison of where you are now, when you just were, and where you think you're going to be that gives you this psychological feeling that you're flowing through time. And ultimately, that's because entropy is increasing. That's where that distinction comes from. Anonymous says, could you talk about any proposed links between gravity and electromagnetism? I'm sorry, Anonymous, that's a little bit too vague for me to give a very explicit answer to, but I wanted to address a little bit for two reasons, or sort of in two different ways. One way is if someone had the idea that somehow magnetism was either part of gravity or the explanation for gravity, okay? So that is an idea that people have had, and that idea is not correct. They're similar. There's relationships between gravity and magnetism, but they're not the same. Einstein tried very hard to unify gravity and electromagnetism. These days we think that was a little bit misplaced because he was trying to say, let's ignore the nuclear forces, and you probably can't do that. But gravity and electromagnetism, as we currently understand them, are certainly different but analogous in some sense things. One of the reasons, the biggest reason why they're different at the practical level is that electromagnetism has both positive and negative charges, whereas gravity only has positive charges. Gravity only ever attracts. One particle only ever attracts another particle, never pushes it away. There's no negative gravity particles in the universe. And that's crucially important for the difference between gravity and electromagnetism. The other aspect of the question is, in the world of electromagnetism, there's electro and there's magnetism. So there's one underlying thing going on, but there is sort of a manifestation of that thing in the form of the electric field. And there's a different manifestation of it in the form of the magnetic field. And this was all unified by Einstein, basically, right, in the special theory of relativity. The beginning of the unification went back to Maxwell, but really understanding them from the point of view of relativity is the ultimate way to go. And so you could ask, is there a similar decomposition in gravity? Is there sort of electrogravity and magnetogravity? And the answer is yes. It's a much less relevant fact because magnetism becomes important when charges are moving fast, right, close to the speed of light. Therefore, gravitomagnetism would become important when gravitating objects are moving close to the speed of light. But gravitating objects tend not to do that. I mean, photons do it, and photons move at the speed of light, but they're so tiny that they don't make a big gravitational field. Things that make big gravitational fields tend to be really heavy and slowly moving. So typically, usually, unless you really care about details of black holes, it is the electrical version of gravity that matters for what you observe in astronomy in our everyday lives. Riverside says The Economist magazine just pronounced in a long article about the state of quantum physics that your and Brian Swingle's modeling of entropic gravity with the use of quantum information theory is the closest thing that may put string theory to the rest. Such journalistic simplifications aside, the LHC and Fermilab muon experiments do seem to retire supersymmetry as a viable experimental outcome, while quantum entanglement becomes a more experimentally promising area. Are we looking at the possible way out of an impasse? Will the mathematical apparatus of the string theory somehow become scavenged and reused as part of entropic gravity entanglement information theory field? A lot going on here also. Let me try to break things down. So yeah, there's a nice article in The Economist. You need to subscribe to The Economist, but that's okay. I'm a believer in subscribing to things and supporting journalism. They did a nice article on the state of quantum gravity and how string theory is a little bit stalled, and some of us, Brian Swingle was mentioned, are trying to, and I was mentioned, trying to build up quantum gravity from quantum mechanics and quantum information theory. So let me say, by the way, it's not just me and Brian Swingle. It's even when it's me, it's certainly me and my collaborators, Charles Zhao, Spiros Mikalakis, Ashmeet Singh, Aidan, who I already mentioned, and a bunch of other people have been involved in this project with me. And then there are other people like Steve Giddings, Tom Banks, who have been working on this for a long time also. So there's a smaller number. It's not like the tidal wave sweeping the world. There's nowhere nearly as many people working on this as there are on more conventional string theory, but we exist. Okay. That's one thing to say. And I'm very optimistic about it. You've heard me say I'm optimistic about it. But there's a long way to go. We're not close to a breakthrough as far as I can tell. The second thing to say is I'm confused as to why you write LHC and fermion muon experiments seem to retire supersymmetry. I think it's exactly the opposite of that. The recent experiments seem to show anomalies in the behavior of muons, their decays and their coupling to other particles, which could be signatures of supersymmetry. Like, we don't know yet. We don't even know if those experiments are going to turn out, if those anomalies are going to turn out to persist over time, but they certainly don't rule out supersymmetry. Third thing is, even if they did, even if they were not related to supersymmetry, even if we just don't find supersymmetry at the electroweak scale, it's still absolutely possible that superstring theory is right. Superstring theory requires supersymmetry to make contact with the physical world, but it doesn't require that signatures of supersymmetry are accessible to us experimentally. They could be up at the Planck scale, or they would be completely inaccessible. Now, it's true that for many, many years, people have focused their attention on versions of supersymmetry that are experimentally accessible. That's not necessarily because those are the best models. It's because being experimentally accessible is important, and we care about it. We want to do the experiments, etc. As I've said before, the fact that we haven't found supersymmetry at the LHC or elsewhere should lower your credence that supersymmetry is true, and therefore lower your credence that string theory is true. But it might not lower it by a lot. That depends on what your priors are and even some difficult to calculate likelihood functions. Finally, will the mathematical apparatus of string theory become somehow scavenged? Look, on the one, let me emphasize, string theory is not dead. It might still be correct, but more importantly, even if it were dead, we've learned a lot by doing string theory. All of the stuff on ADS-CFT and holography and all that stuff grew out of string theorists. Not to mention string theory trying to understand condensed matter systems or strongly coupled nuclear systems or other things like that. So what we've learned from string theory will continue to be useful down the road. Richard Graff says, you convinced me that emergence, I'm grouping a bunch of questions together here. Emergence is the key to understanding how the quantum world manifests in the macro world we experience. But what is the state of emergence study? Has it coalesced into what could be called a science or math of emergence? Andre Mirabelli says, it seems easy to think about how rules about gliders emerge from rules about grid occupation. That's a reference to John Conway's Game of Life, the cellular automaton that is very famous. And laws about liquidity emerge from laws about molecules. It is harder for me to see how the very existence of particles emerges from laws about the probability amplitude wave for states or particles. It is still harder for me to see how the experience of awareness emerges from material laws. Can you provide some guidance for how to more specifically think about emergence in ways that can make its meaning clearer in these seemingly more powerful senses? John Stout says, I'm grouping 4 questions together here. So number 3 is John Stout says, emergence. Can you explain this to me in more detail? It is difficult to grasp how to label one or another effect as emergent. Basically, it's a similar question to what Andre just said. And then Josh said, when you reason about emergence phenomena, are you merely using a shortcut to reason about the underlying structures? Or is there a sense in which understanding at the level of phenomena is different than merely being able to reason about how the constituent parts fit together? Like, for example, do humans who understand concepts like center of mass and democracy have a sort of understanding which Laplace's demon could never have? So yeah, this is so there's a bunch of things here about emergence and what it is and where it's going. So I said this before, I'm sure, but let me try to summarize how I think about this idea of emergence. It's not a great word, emergence. Let me put it that way. When I was first writing the big picture, and I was using emergence all the time, like on every page, many people, especially philosophers, but also sociologists and others, said, oh my God, don't use that word. It's too overburdened with different meanings, and it means different things to different people, and it will just be confusing. And I thought I almost didn't use it, but once the cat's out of the bag, it's very, very difficult to invent new nomenclature for things. People use the word emergence to talk about this stuff. Here is why it can get confusing, because physicists think about emergence as saying that there exist, everyone who thinks about emergence thinks about the world in terms of levels, okay? And the level metaphor is a little bit misleading in its own right, but let's, for right now, go with it. So there's sort of microscopic levels where you talk about particles and fields and forces, etc. Very, very tiny things coming together to make bigger things. And there are macroscopic levels, whether it's chemistry, biology, humanity, sociology, astronomy, what have you. And what the physicist will say is the different levels might very well speak different vocabularies, use different words, right? The vocabulary we use to describe human psychology is very different than the vocabulary of the standard model of particle physics, or the core theory, if you like. But the physicists would say they're compatible. It's just that the higher level emergent description is taking advantage of the existence of patterns that simplify things that are implicit in the lower level dynamics. So in other words, that's why I like to use the center of mass of the Earth as a special example. You don't need to know all the positions and velocities of the particles in the Earth to predict its motion around the sun. You only need to know the center of mass, position, and velocity. But that's not easy or obvious or necessary, right? That's a special miraculous thing about the laws of physics. You are throwing away almost all the information and still making good predictions because the information that you're keeping, the center of mass, position, and velocity, is really, really, really specific and special, okay? So if you had thrown away random information, you'd be able to predict nothing. Like, let's say you threw away all of the positions and you kept only the momentum of all the particles in the Earth, right? So you know the average momentum of the Earth, but you have no idea where it is. So even though you're now keeping half of the information, you make zero predictions about where the Earth is actually going to be. And that's the generic situation. If you just keep some fraction of the information about the underlying system, it does not allow you to predict anything at all, roughly speaking. So emergence in this physicist sense is a special, wonderful, extraordinarily useful feature of nature, of reality, that there exist these other ways of talking about the world that are, from the point of view of the microscopic theory, woefully deficient in information and yet capture something real. Dan Dennett called these features real patterns that really exist there. Now, there are also other people in philosophy and sociology, et cetera, communities who think about it very much the other way around. They think that they use emergence to mean explicitly cases where there are behaviors in the macroscopic level that cannot be understood in terms of just the microscopic level, something that is truly new. So you couldn't put the microscopic theory on a computer, run it, and get the right answer, because there's something truly new. That's the idea of strong emergence in some classification schemes, okay? So I never mean strong emergence. I only mean weak emergence. So to get to Andre's question and to John's question, that's what I mean by emergence. It's a little bit, so the point is that, well, actually, let me get Richard's question first, because maybe this will help. There's a lot we don't understand about emergence. Richard is asking, what is the state of the study of emergence? There's a lot we don't understand. And the basic reason why there's a lot we don't understand is because if what you want to understand is particle physics, the best way to make progress is to study particle physics. If what you want to understand is biology, the best way to make progress is to study biology. And if you want to understand psychology, the best way to make progress is to study psychology. So clearly all of these different levels have to be compatible with each other, but studying the ways in which they're compatible is very much less common than just studying the levels in and of themselves. And because we can just look out the window and see human beings and big macroscopic structures, we take for granted that they must be explicable in terms of atoms and so forth without ever actually doing the work to say, what is the general theory of when is there an emergent description? When is a macroscopic theory compatible with microscopic theory and all that stuff? So I would say that there's a lot of work to be done in the theory of emergence. We'll be talking about it in upcoming podcasts. I think it's important and interesting. But there are people studying it, right? I guess that's the point. Like I said at the beginning, this is part of why I'm here in Harvard. Ned Hall, who is another Mindscape guest and is sort of my host here in the philosophy department, jokingly said over email, while you're here in the fall, let's figure out emergence once and for all. So we're going to try to do that. I'll let you know if that happens. But okay. But the point is, so that's the state of emergence. Namely, I think it's young and still underdeveloped. But this fact that we can cheat by seeing the higher levels immediately, or just using our eyes rather than always starting with the lower level and deriving the higher level, means on the one hand we can talk about different levels without understanding emergence very well, but also it makes the phenomenon of emergence sometimes hard to understand. Because there's part of us, especially if we know about examples like fluid mechanics, right? Like fluid mechanics emerges from atoms and molecules. There, we can derive fluid mechanics from atoms and molecules. You can literally go from the microscopic theory to the macroscopic one, or the center of mass motion of the Earth. You can derive that. Isaac Newton did it. Whereas, so that gives you the impression that what emergence is about, or what the study or use of emergence is about, should be somehow deriving the higher levels from the lower levels. And that might be arbitrarily hard. The levels need to be consistent, but it might be effectively impossible to derive them. That doesn't mean that it couldn't be done, but we human beings can't do it or something like that. And as a result, the emergent levels can involve concepts and vocabularies that are entirely different from the concepts and vocabularies at lower levels. That's even a little bit true even for liquids, right? For fluid mechanics. I mean, we talk about temperature and pressure and density when we talk about fluids. None of those rules is there. None of those words is there at the level of atoms, individual atoms and molecules. And so we don't make a big fuss about it because we're so used to it, but it's exactly the same for classical particles emerging out of quantum mechanics, or for humans and their psychological properties emerging out of biology and ultimately from physics. Don't think about a direct route from the microscopic theory to the macroscopic theory. Think about both theories existing, and as a research program, find the connections between them. That's a better way of thinking about how emergence actually works. Finally, Josh asks a very good question. Does emergence give us human beings some insight and understanding that Laplace's demon wouldn't have? After all, Laplace's demon knows where all the particles are, all their positions, all their velocities, and can predict where they're going to be in the future. So is there some sense in which Laplace's demon knows everything, but only at the microscopic level? I don't want to speak for Laplace's demon. I don't know what Laplace's demon knows and doesn't know, but I know what you mean. The reason why I say I don't want to speak for Laplace's demon is I don't think that the thought experiment is perfectly well defined. Like, no one has ever agreed on exactly what capacities and abilities Laplace's demon has. So I could easily imagine Laplace's demon just knowing the microscopic laws, right? Just knowing the most comprehensive fundamental level of reality and not realizing that there were these simplifications. I mean, after all, if you have the exact solution in your head, who cares about the simplifications, right? But I can also imagine a version of Laplace's demon that understood not just the microscopic level, but every possible level of the emergent descriptions of reality. So I don't know. I think that those are different versions of Laplace's demon, but none is the right one or the wrong one. Okay. Spoonly Orange says, if a particle is a wave in a quantum field, does it also exert a force on the surrounding field towards the center of the wave? For example, a standing wave on a string held between two clamps exerts a force on the clamps toward the center of the wave. Yes, it can. They can, right? In fact, there's a very famous phenomenon called the Casimir effect, which is exactly this. You don't even need particles. You can just have waves, the quantum fields in the vacuum. And what you say is that if you imagine two parallel plates that are perfectly conducting, right? So what that means is if the plate conducts electricity perfectly, it's a superconductor, then electric and magnetic fields cannot penetrate, electric fields cannot penetrate inside. So it cuts off the different wave modes that you can have in the space in between the two plates. And it turns out that the existence of some modes of the quantum fields, but not others, in between the plates, exerts a force on them. I don't want to say it pulls, because sometimes it pushes. It depends on whether the fields are bosons or fermions. But this is something which you can actually test experimentally. And then there are philosophical arguments about whether it's really the vacuum modes or whatever, but I think the most straightforward way of thinking about it is exactly that. So in that sense, yes. Douglas Albrecht says, would you mind providing an explanation of what energy is, especially as it relates to the quantum? Is it mass? Is it field frequency? Is it momentum? In its essence, what is energy? So it's none of those things. Energy. I think the right way to think about energy, it doesn't even matter quantum versus classical. Energy is a property. I think it's a mistake to start thinking about energy as a thing. And I know why people would think about it as a thing, because it's conserved. So, if you have a bunch of water and a bunch of pots and pans, the amount of water is conserved as you pour the water from one pan to another, right? And so you think of the water as a thing, and it's conserved. And since energy is conserved, it can be transferred from one thing to another. It's kind of tempting to think of it as a substance in some sense, but it's not. What's a substance are the stuff. Substances are the stuff in the universe, particles and things like that, right? So we talk about the energy of a particle. Particles can have kinetic energy and potential energy, et cetera, right? So it is a property of a particle or a field or a bunch of particles. And what property is it? It's the property that is conserved because the laws of physics are invariant under time translations. This is Noether's theorem. Emmy Noether was the mathematician who proved that when there is a symmetry of nature, there's an associated conservation law. And the laws of physics have a symmetry, namely they're the same laws at every moment in time. There is no force outside the universe twiddling a knob, changing the value of the fine structure constant or the mass of the electron or anything like that. These are constants of nature, at least within our observable universe. And so because of that symmetry, because of time translation and variance, there is a conserved quantity, and it's the energy. That's what it is. And now if that's too abstract for you, then all you have to do is say, well, give me a physical system that you define very carefully, and I can figure out what the energy is. If it's a ball rolling down a hill, there's a kinetic energy and a potential energy, etc. That's the formula I would use to calculate that property that the ball has, and that is what energy is. Jeffrey Siegel says, I seem to recall in a previous AMA that you mentioned that most of the expansion of the universe is occurring between galaxies, with dark matter appearing mainly between galaxies. I got the impression this is not simply because galaxies are flying off in many directions, but rather that space is indeed expanding between the galaxies. If that is correct, is there a theoretical reason for space to be selectively expanding between galaxies? So I want to get rid of the phrase dark matter that somehow appeared in the middle of that question. That has nothing to do with dark matter. There's more dark matter in the galaxies than in between the galaxies. There's some dark matter in between galaxies, but it collapses and concentrates just like ordinary matter does in galaxies and clusters of galaxies. Is there a reason for space to be expanding between the galaxies? Yes, but it's kind of the other way around. It's not that space expands between the galaxies. It's that inside galaxies, space isn't expanding anymore, okay? In the early universe, where there were no galaxies, everything was more or less smoothly distributed, everything was expanding. Space was just expanding. But there were regions where there's a little bit more matter than elsewhere, a little bit more gravity, and that gravity pulled things together. And once the matter sort of stops moving apart, and the overall local gravitational pull starts pulling them together, at that point, it is no longer meaningful to say that the expansion of the universe is having any effect whatsoever inside that region of space. So I think that the better way of thinking of it is space is expanding everywhere except where there is a galaxy or some other concentration of matter. And now for something completely different, we have, I'm going to group two questions together about relationship advice. Relationship advice is something, again, that I'm not an expert on, but do have experience with, so why not? Casey Mahone asks, how can you tell whether a relationship is worth fighting for? And Michelle, to group it together, says, what is your advice for dealing with people who are condescending and self-important? I don't, by grouping these together, mean to imply that Casey's relationship is with someone who is condescending and self-important, but there are certain commonalities between these two questions. And, again, I'm not in any sense qualified to give empirically evidence-based answers to these questions, but my own personal impression is that if I've learned anything about people in the context of relationships, is that people don't change that much that quickly. I do think people can change. People certainly do change. People when they're 50 years old are not the same as when they were 20 or as when they were 5. It's just obvious that people change. But there are certain commonalities and major changes, the kinds of which would have a large impact on a close personal relationship, are rare. And therefore, the older I get, the more my philosophy of relationships is just have relationships with good people from the start, rather than having relationships with not good people and trying to fix them. So the relevance of this observation to Casey's question. How do you tell whether a relationship is worth fighting for? I mean, part of me wants to say almost never. It depends on exactly what kind of situation you're in, but and what you mean by fighting for the relationship. Do you mean someone wants to leave you and you're going to fight to keep them? You're going to sort of try to convince them that it's right? Almost never would I try to do that. If they're still maybe interested and just not sure, then by all means talk it out, try to figure out what's going on, how you can be better. But if they want to leave, let them leave. Do something else. Get another person. Find someone who is a better fit with you from the start. I mean, it's not that people are stuck and can never change, and therefore relationships can never change. But rather than fighting for the relationship or trying to change the other person, it seems to be much more fruitful to try to look inside yourself and ask, what is it about you that is not making this work? What is it that you can improve? Changing yourself is really, really hard, but it's much easier than changing other people. Now, on the other hand, if you're two people who are very much want to be in a relationship, but there is some particular aspect of it that is not working, right? So it's not that you're fighting the person who wants to leave. You both want to stay, but there's something that's not working. That's worth trying to do. Try to figure out, are there parameters that you have where you can both alter your behaviors in ways that fixes things. But often there are just incompatibilities. And, I've often seen with people I know, what they look for in a person is not what they really need in a person, right? They're looking, when they're out there on the market, they have a checklist and they want to go through the checklist. But then when they're in the relationship, what they actually want and need is something very, very different. So you have to be open to the possibility that there were sparks flying there at the beginning, and yet now it is not worth rekindling those sparks. And I hate to be a downer about this, but there's a lot of people out there. And when we're talking about romantic kinds of relationships, I think that the usefulness of your time is much better spent finding the right person for you rather than trying to fit somebody else into a situation that doesn't quite work for them. Someone else will be right for them, hopefully. And then Michelle's question, the reason why this is related is not because the questions are related, but because the answers are related. Michelle's question was, how do you deal with people who are condescending and self-important? The answer is, to any extent possible, you don't. Don't try to fix them. Don't try to offer witty one-liners that will, bring them down to ground. Don't try to explain why this is a not good way to be, unless, they're open to that. Some people are open. Some people make mistakes, sure, and are willing to fix them. But other people like being condescending and self-important. That's kind of their shtick. That's kind of who they are. And I would say just don't hang with those people to any extent possible. Sometimes it's not possible, right? It's your boss or it's your student for that matter, right? It's someone you have a relationship with for some external reason that you can't get rid of. So in that case, I think that condescension and self-importance are kinds of flaws that are not closely related to any real virtues, right? Other than being awesome. Like if the person is awesome and that's why they're self-important because they really are important, then, what can I say? But more often, it's not like, someone is a workaholic, right? Where workaholism has positive aspects and negative aspects. Even being lazy can, in some sense, have positive aspects or negative aspects, the flip side of being a workaholic. But being condescending and self-important is just bad. So typically, people who are really characterized by those personality traits aren't going to change them. That's just who they are. And so if you can't minimize your dealings with them and contact with them, I would try to minimize your responses to them. Just let it roll off your back to the extent that you can, Twitter is a great training ground for this. If you can ignore people who are saying dumb things on Twitter, condescending and self-important things, for example, then you could ignore them anywhere because your real life barriers to trying to strike back are much greater than they are on the internet for whatever reason. I don't know. So I don't know whether Michelle or Casey, whether that my advice in either one of those cases is very actionable and helpful to you, but it's my attitude. Again, as I get older, as I've seen things, as I've lived my life, life's too short, man. It's too short to be with the wrong people in the wrong situations. We spend far, far too much time trying to fix a bad situation rather than trying to find a good situation. And that's a very overgeneralized statement, but I'm sticking to it. Antoine Chopin says, congratulations on your new role at Santa Fe Institute. You told us your research focus would be on complex systems. Could you give us a glimpse on what it is, and how it relates or not with what you've studied so far? So I could have grouped this with the emergence question, actually, because that's the basic question. Complex systems is itself a pretty broad field. If you go to Santa Fe, one of the great things about the Institute is there'll be archaeologists, there'll be economists, there'll be physicists, there'll be computer scientists, there'll be philosophers. It's an enormous range of traditional disciplines that have something to do with complexity in some way. And so likewise, the field of complex systems is itself very, very big. So my specific kinds of interests within complex systems are the sort of general structural questions, the quasi-philosophical questions. So just like within physics, I'm much more interested in general principles than in specific physical systems, this or that particle or planet or material or whatever. Within complex systems, I'm much less interested in this or that complex systems and in rules by which we can somehow find commonalities between very, very different kinds of complex systems. And in particular, I would say that to specify it a bit more, my current research interest is in relating the lowest, most fundamental level of physics, which is where I've spent most of my life studying, to levels above. So entropy is a huge role in that, right? The arrow of time is a huge role in that. But the very idea of emergence is exactly this idea, right? How you can relate different levels to each other. Are there causal relations between them? Are there supervenient or entailment relations between them? In what situations? In what are the criteria by which you say that emergence can happen? Does it happen the same time all the way? When you go from small numbers of particles to large numbers of particles, sometimes there are emergent phenomena, sometimes there are not. Sometimes those phenomena are complex and sometimes they're not. Like a bucket of water has a lot of particles in it, but it's not complex all by itself. So what's the difference? What are the criteria you need to say that something is complex and how it will operate? And once you have those things, can you use them to say things like, how are economies similar to the nervous system or to the internet or something like that? That's the kind of thing at the very broadest scale that I would be interested in. Okay, so I'm going to group together, there's a whole bunch of questions on decoherence. Maybe this is just random quantum fluctuation, or maybe it's because of the David Wallace podcast, but a bunch of questions. So Joseph Dundee says, what is the relationship between decoherence and measurement? They seem almost like the same thing to me. Marco Tauser says, as I understand it, decoherence can be thought of as due to the leaking of information from a system to its environment. This is why Schrödinger's sleepy-wakey cat is already decohered long before we open the box. The information about the cat leaks through the walls of the box within a microsecond of when the superposition is first established. My question is, can there conceivably be anything that we can make the box out of so that the information doesn't leak out? Does nature allow decoherence shields? Bill Warner says, can you help me understand decoherence? That's a very basic question. I can't picture a diagram for it in either Copenhagen or many worlds. Benjamin Barbrell says, my question is about the measurement problem in quantum mechanics. This problem arises from trying to find the boundary between classical and quantum behaviors. I understand that decoherence essentially solves this problem. Am I right to put it like this? How complete is our understanding of decoherence? Is it still the object of theoretical or experimental research? So there's a couple things going on here, as usual. As a phenomenon, decoherence is pretty well understood. It is, there are details about when it happens, how you can avoid it, how quickly it happens. Those are all good technical questions, but the idea is pretty solid. Namely, you often, very, very, very often find yourself in quantum mechanics in a situation where you have a system of interest, cat, an atom, spin, whatever, and you have an environment. You have the whole rest of the world. And of course, even in classical physics, you had an environment. But the difference is, in classical physics, you could go to a regime where the environment didn't matter, where you did in fact shield it off, as Marco suggests. if I'm standing here and I'm being bombarded by photons, if you turn off the lights in the room and I'm not being bombarded by photons, I don't change that much in any particular way. Whereas in quantum mechanics, the environment becomes entangled with you very quickly. So you can't not include the environment. And that process of becoming entangled with the environment is what decoherence is. So you basically say, I have the system, I have literally everything else in the universe, and I say, does the system stay unentangled with everything else, or does it become entangled? If it becomes entangled, that's decoherence. If it does not become entangled, it's coherent. That's the maintenance of quantum coherence. So, Bill, you want a picture of it, a diagram. I'm not sure how to do that. Usually this might be a bit too hardcore on my part, but usually to these kinds of questions, I say, too bad. There's no diagram for this. Not everything can be visualized, especially in quantum mechanics, where things are many, many dimensional, right? Far more numbers of dimensions than we can plot on a piece of paper. But if you want a picture, the picture is just this: a picture of Schrodinger's cat awake, entangled with an environment that is interacting with it, and Schrodinger's cat asleep, entangled with an environment that is interacting with it. That's basically what you should picture in your mind. What is the relationship of this to measurement? Actually, let me first answer the other questions. Marco says, can you shield decoherence? Well, yes and no. You can't shield decoherence for a macroscopic system in the real world. The cat in the box is a system, but the photons and air molecules in the box count as the environment. It's not only the environment outside the box. In fact, usually when I say that decoherence happens long before you open the box, I'm thinking about the parts of the environment inside the box, that are going on. Having said that, if you wanted to be more general about it and just ask the question, can you shield one kind of system from becoming entangled with another? Yes. This is the job of quantum computer builders, because to do a quantum computation, you need multiple qubits, which entangle with each other, but not with the rest of the world. You want to shield them from decoherence. That's exactly what you want to do. So you make everything very, very cold. It's harder than you think, because you can say turn off the light so there's no photons, but at room temperature, everything around you is glowing. If you put on your infrared goggles, you'd see that there's actually lots of photons in the room. There are radio waves and things like that also. So it's harder to shield out photons than you would think, which is why it's harder to shield out decoherence than you would think. The other two questions is about the relationship between decoherence and measurement. The reason why the relationship is fuzzy is because the word measurement is fuzzy. The word decoherence is not fuzzy. We know what decoherence is, but measurement is something where we say we know it when we see it, like I've measured something, but what is actually physically happening during the act of measurement will be different depending on your favorite interpretation of quantum mechanics. So because your favorite interpretation is obviously the Everett interpretation, there's a very, very close relationship between decoherence and measurement. But in other interpretations, it might not be. So if there were no other interpretations of quantum mechanics and Everett were just accepted as correct, then there would be a very close relationship. Basically, what we think of as human measurement is just one subset of the larger numbers of things that can happen where a system becomes decoherent, and you might as well call all of them measurements. It's different than interactions. I think maybe someone else asked about the relationship between measurement and interaction. You can interact something without becoming entangled with it. If I have a spin that is in a superposition of spin up and spin down, and I just pick it up and move it, but I don't measure the spin, I have interacted with it, but I've not become entangled with it. So it's not a measurement. It's not decoherence going on because the entanglement didn't happen. Rebecca Lashua says, are all physical phenomena computable? Most real numbers are not computable, and only a countable subset of them is. Does this mean that space-time is much smaller than R4? R4 is the four-dimensional, smooth Euclidean space. Do you think the universe is necessarily computable, i.e. that is incoherent to imagine existing within a universe that can't be computed by some algorithm? I think that the issue with this question is we haven't quite defined what we mean by computable in the following sense. Obviously, there are definitions of what we mean by computable. And when you say the phrase, most real numbers are not computable, that refers to a specific definition of what computable means, namely ways to calculate numbers. And as you say, most real numbers are not computable. There's no algorithm you can write down that would specify that particular number. It's a kind of counterintuitive thing to those people who have not studied analysis or topology, but the real line has a lot of numbers in it. Let's put it that way, more than you think. And so, but that notion of computability doesn't immediately translate to physical phenomena, right? Like, what do you mean by are all physical phenomena computable? Like, here's a physical phenomenon. When I let go of the coffee cup in front of me, it lands on the table and doesn't fall through. What does it mean to say that's computable? I mean, it's predictable, but do I need to specify the literally exact location of the coffee cup? Do I need to, be Laplace's demon somehow? Like, I don't know exactly what that means. It seems, as we've already talked about, to be a feature of our physical universe that it obeys rules, right? It obeys the laws of physics. So in that sense, it's computable. But the thing that is computing it is the world. So the world itself can be thought of in some sense as a computer, going from one moment of time to the next. But it does uncomputable things in some sense. If the laws of physics were just Newton's laws of classical mechanics, space is a continuum that is part of the definition. And whether that's physically right, I have no idea. But I don't have any obstacles to imagining things like that being right. And the fact that I can't write a computer algorithm for every single possible real number doesn't get in the way of doing that, as far as I can tell. So I'm not sure if that's a satisfying answer, but that's how I think about these questions. You just need to be a little bit more careful about what you mean by computable. Brandon Lewis says, what topics or concepts in mathematics beyond calculus do you find useful in theoretical physics? Well, many. You can buy fairly thick textbooks called, mathematical methods for physics or for physical sciences or something like that. And these books usually talk about ideas past simple calculus. You'll take a class in calculus where you learn derivatives and integrals. The mathematical methods courses will then do vector calculus, complex numbers, so complex calculus also, but then also maybe linear algebra, so matrices and vectors, a lot of differential equations and solutions to differential equations, which in some sense is part of calculus, but so much material there that you need another course to talk about it. And then a tremendous amount on transforms of functions, right? Fourier transforms, Laplace transforms, turning data in one space, like position space, into data in another space, like momentum space or frequency space and things like that. So the grab bag of different techniques. And then even beyond that, you'll find other books for more advanced students called things like geometry and topology for physicists. And then you learn something about Riemannian geometry and homotopy and homology and fiber bundles and things like that. So there are a lot of concepts in math that are very useful in theoretical physics. It depends, of course, on what kind of theoretical physics you want. I didn't even mention statistics, but that's just taken for granted. Vincent Ohm says, will we ever be able to understand the nature of consciousness, do you think? What is the likely road toward this understanding? I think so. I think we will. I mean, why not? Like, whenever someone says, will we be able to understand the nature of X? I'm saying, yeah, sure, why not? I mean, maybe. Now, there are plenty of things that we haven't yet understood, and there's a temptation to say, well, we haven't understood it yet, therefore maybe it's not possible to understand. But, you could have said that 100 years ago about a million things that we do understand now, right? So that's not a very good argument. Consciousness is one of the hardest things to try to understand because it's an emergent phenomena from one of the most complex systems that we know about, the human brain and body. So the fact that we don't understand it yet is the least surprising thing in the world. What is a likely road toward this understanding? Doing neuroscience mostly, some combination of neuroscience and philosophy and psychology. But I can't be more specific than that because, number one, I'm not a neuroscientist, but number two, it's in the nature of science to not know exactly what steps you should take to get to the answer you're looking for. You just got to take steps and try things and guess and see what works. Brandon Lewis says, the phrase shut up and calculate comes up from time to time in discussions related to theoretical physics. What sort of calculations are usually being alluded to when this phrase is invoked? So this phrase was invented by David Mermin, who is a physicist at Cornell, when he was trying to characterize a certain attitude that some people have, not him, but some other people have toward quantum mechanics. Some people like me and like David Mermin really want to understand the foundations of quantum mechanics in a deep way. Sometimes we even end up talking to philosophers about it. Other people say, look, we can use quantum mechanics just fine. We can predict the lifetime of the neutron or the scattering rate of something or the high temperature superconductivity phase transition or something like that using the rules of quantum mechanics. And to do that, you need to do a calculation. Right? There's some integral, you calculate the amplitude of some possibility, you square that amplitude to get the probability, right? That's what you calculate in quantum mechanics. Those are the kinds of calculations that are being talked about. So it would depend on the specific system you're studying, but it's just typical physics calculations. Sid Huff says, in a previous podcast, you briefly mentioned the book Quiet by Susan Cain about introversion and the challenges often faced by introverts. So are you an introvert? And if so, how do you think this trait has affected your professional career, research, teaching, etc.? So I think I am. I'll be very to be fair, to be honest, two things. Number one, I haven't read Susan Cain's book. I've read a little bit of it, and I've read excerpts and heard people talk about it, so I'm familiar with the basic idea, but I haven't read it. And as a book writer myself, I know better than to mischaracterize what is in other people's books. And secondly, second caveat is there's research beyond what she wrote about in the field of introversion and extroversion, and controversies about that research, and I'm not familiar with that either. So rather than trying to be too careful about the definition of introvert, the one insight that a lot of people really appreciated from that discussion, and I don't even know if it was original to her or she was quoting somebody else, but the idea that rather than thinking of introverts as shy people or antisocial people, you can think of introversions as people who it costs energy for them to interact with others. Whereas extroverts actually gain energy. If they're interacting with others, they get excited and it juices them up. And if they're left by themselves, they kind of sort of get antsy and uncomfortable. Whereas introverts need to recharge. They need to be alone and have their alone time. And then in the right circumstances, they can go out and interact with other people. I'm not sure if that's now the accepted definition of introversion, but that's the takeaway that I had from the discussion around that book. And by that definition, I'm absolutely an introvert. I absolutely need to be alone to recharge. I'm not someone who, so after I give a talk, if I give a public talk or whatever, I would really just like to go back to my hotel room or whatever it is and have some me time. I'm not out there to party afterward. I'm exhausted usually afterward. I can do it. I can do small talk at parties. I can talk pleasantly to people I don't know. I can give lectures. I can talk on TV. I can have a podcast. I can do all those things. But it wears me out, right? So I don't know. If that counts as being an introvert, then yes, I am introverted in that sense. How's it affected my professional career? I'm surrounded by fellow introverts, so it hasn't affected it that much at all. There are people who, within academia or within physics or within science, take more and less pleasure out of teaching and outreach and giving talks and things like that. And I like giving talks a lot. I have a podcast. Come on, it's pretty obvious that I like interacting with other people a lot. But I didn't start out being any good at it. I wasn't, a natural or anything like that. I was terrible at it when I first started many, many years ago, and I have worked to get better at it. And there's a lot of people in academia who just don't bother to work to get better at it, so they remain not very good for their whole lives. So I think a lot of people in academia are natural introverts, but some of them have gotten very, very good at interacting with large groups of people or maybe even small groups of people. Moshe Fader says, this goes back to an editorial conference I had with a new author over a decade ago. We were talking about future projects, and he described a science fantasy novel he'd done a little work on. It involved 2 inhabited planets, or maybe a planet and its large moon, that powerful sorcery had brought gently together until they nearly touched, just a few miles apart. My question for you is, what would happen if the magic failed or was turned off and normal physics restored? Obviously, the two bodies would immediately close the small distance between them, but then what? So, two pieces of bad news for you. One is they would not immediately close the small distance between them. It depends on how they're moving, right? If the two bodies are revolving around each other in a common orbit around their center of mass, then, in some idealization where we forget about tides and friction and things like that, they would, if they were doing it at the right speed, they would stay exactly at that distance between them, just like the Earth and the Moon stayed roughly the same distance. Not exactly, because the Moon and the Earth both rotate as well as revolving around each other, and there are tidal friction forces that actually gradually pull them apart. So if the two planets were not tidally locked with each other, then they would probably gradually drift apart, actually. Of course, if they were not revolving around each other, if they were not moving, they would just smash into each other and everyone would die, I guess, if they were living on the planets. That would be bad. The other piece of bad news is that the novel has already been written. It's called Roche World by Robert Forward. Robert Forward, one of my favorite science fiction authors, not because he's a great writer. He was not a great stylist, let's put it that way. But he was super duper imaginative. I think a professional physicist or engineer or something like that. So he wrote Dragon's Egg, which is about life on a neutron star. And one of his other novels called Roche World, or alternative title, The Flight of the Dragonfly, was literally about two planets that were so close together that they shared an atmosphere and even oceans and things like that. So that has been explored, and there's no magic involved. It was purely science fiction, if you want to check that out. Thies Janssen says, could you play devil's advocate and explain why interpretations other than the Everettian interpretation exist? Well, there's two aspects here. One is, the psychological aspects of people just not liking the Everett interpretation, okay? So that might mean they don't like the idea that there are a lot of other worlds, or they don't like that the existence of these other worlds is unobservable to them, or something like that. It just rubs them the wrong way. I think those are real. It's very far from our experience, and it's not even completely irrational to say that a scientific theory that claims that the real nature of reality is very, very different in its fundamental essence than our everyday experience should be treated skeptically, right? I think that it's okay to start your scientific theorizing close to the phenomena that you observe. And I think there's good reasons to, in the case of quantum mechanics, go far beyond them, but it's okay to start there and to be skeptical of ones that go far beyond it. But that's a, kind of more, like I said, psychological worry. There are also good physics worries, and I think that there are two very good physics worries about the Everett interpretation. One is the probability question. In ordinary quantum mechanics, certain things happen with certain probabilities. In Everett, everything that can happen, everything for which you would ordinarily assign a non-zero probability, actually does happen in some branch of the wave function. And so how do you recover the physical information, the data, the experience that we have of the world, that if we measure spins over and over and over again, we get a certain fraction of them being spin up and a certain fraction being spin down that we can predict very accurately, right? Now, I think there's an answer to these questions. In fact, I think there's more than one good answer to that question. Famously, David Deutsch and David Wallace used decision theory to derive a proof that you get the usual predictions. Chip Siebens and I developed another idea based on previous suggestions by Lev Weidman and others that use self-locating uncertainty. So I think it's an answerable question, but I get it if you're not completely convinced. It's tricky, and it involves philosophy as well as physics. And the other question, which I think has gotten even less attention, which is what I am mostly thinking about these days, is what we call the structure question. Every other interpretation of quantum mechanics has a wave function, the Schrödinger equation, and extra stuff, okay? That extra stuff might be other hidden variables or extra rules about how wave functions spontaneously collapse or something, right? Some notion of what is observable and what is not observable, for example. Whereas in the purest versions of Everettian quantum mechanics, you just have wave functions and the Schrödinger equation. You don't have any extra stuff. So the journey from the pristine purity and austerity of Everettian quantum mechanics to the messy specificity of the world is very long and potentially fraught with peril. And not a lot of work has been put into deriving the real world from the bare bones version of Everettian quantum mechanics. So I'm trying, if you are a little bit happy with some equations, you can check out my fairly recent paper called Reality as a Vector in Hilbert Space. And there's a previous paper with Ashmead Singh along the same lines called Mad Dog Everettianism. But the point for your question is, these are perfectly good questions. Like, it's not at all obvious that this idea of taking just a wave function and the Schrodinger equation and deriving the world from it will work. We're doing it. I'm pretty optimistic it will work. I would put good odds on it, but it's not obvious or set in stone. As long as that is true, it's good that other interpretations exist. If I were the boss of reality and science, I would put less emphasis on the other interpretations, but I'm glad that they exist and other people are working on them. Richard Riley says, I'd still like to know just how electrons and protons fuse together to create neutrons during the process of neutron star formation. Does an electron fuse with an up quark in a proton and turn into a down quark in the resulting neutron? Is the mass of the neutron in general equal to the sum of the masses of the proton plus however many electrons it would need, etc.? So, basically, yes. Remember, a proton is two up quarks and a down. The up quarks have charge plus 2/3, and the down quarks have charge minus 1/3. The neutron is one up quark and two downs. So when you convert, let's do the more familiar one. Neutrons decay, right? So a neutron decaying is basically the neutron turning into a proton and an electron and an antineutrino. It needs to be an antineutrino to conserve lepton number and all those things, but it's there. And so that's basically one of the down quarks in the neutron converting into an up quark plus an electron plus an antineutrino. And you can draw little Feynman diagrams to watch it happen. I've drawn those Feynman diagrams in many places, including the Biggest Ideas in the Universe videos, if you want to check those out. So the proton converting into a neutron is basically the same thing in reverse. You go proton plus electron goes to neutron plus neutrino. So really that electron is glomming onto one of the up quarks in the proton, converting it into a down quark and spitting off a neutrino. And that's why when you make a supernova, there's a lot of neutrinos that come out. We've even detected some of them, like in supernova 1987A. The mass neutron is not equal to the masses of the proton plus however many electrons it needs, because there's other things going on. For one thing, the proton and the electron are not necessarily in the same center of mass. The mass of an electron plus a proton is less than the mass of a neutron. So you need more energy than that, especially because you're also spitting out a neutrino. So it's a complicated thing, but don't worry. We have figured it all out. You can figure it out yourself. It's actually not that hard to do what we call the kinematics of those reactions. Neil Glue says, the three spatial dimensions of the universe we live in could go on forever in all directions, or they could wrap around in 1, 2, or 3 dimensions. If they did wrap around in one or more with a circumference less than the size of the observable universe, we might be able to observe that. Do you know of any astronomy or cosmology work considering that possibility, particularly experiments to provide positive or negative evidence for whether the observable universe wraps around? Yeah, absolutely. There's very... I'm not sure if active is the right word, but they were active research programs to look for evidence of a finite universe in the cosmic microwave background. If the universe is finite in size, but wraps around on itself like a torus or something more complicated, then it could be that different parts of the microwave background we look at are actually the same physical location in space, just looked at in different directions. So you can and you do look at that, and people have looked at it and put very, very strong constraints on that possibility. In fact, Jan Levin, who was a previous Mindscape guest, wrote a whole book about it. She was one of the experts in this field. So her first book was called How the Universe Got Its Spots, because in these topologically non-trivial universes, you could get spots on the cosmic microwave background. So she talks about what that would be and how you would go look for it. It's a very good book if you want to check it out. Matt Faw asks a priority question. Remember, I don't know if you've had priority questions yet today, but priority questions are the ones that I promise to answer, but every human being is only allowed one priority question per their lifespan in each branch of the wave function of the universe. As I understand it, space begins to expand at t equals 0 uniformly everywhere. Therefore, it seems like every particle of matter or dark matter would, from t equals 0, effectively move away from every other particle in the universe. As space expands between them, the gravitational attraction between every particle in the universe should also get weaker. If expansion beat gravity at the very first moment, it seems like expansion would always beat gravity, because gravity would just keep getting weaker the further things got from each other. It seems as if expansion should lead to a universe without structure, just a fine mist of rarefied particles. So there's two things going on here. One is I want to be a little bit more specific about what is happening at t equals 0. Specifically, you shouldn't say anything about what happens at t equals 0. T equals 0, by which I presume you mean the singularity in the Big Bang models of cosmology, is a singularity. By singularity, we mean physical quantities become infinitely big, and therefore your theoretical description of them is wrong somehow. We don't know what happens at t equals 0. So if you wrap your brain into knots trying to understand not just the very, very early universe, but literally t equals 0, you're going to come across paradoxes, because many of the things you're trying to attach meaning to are of the form 0 times infinity, or 0 divided by 0, or something like that, including the space between particles and or the size of the universe, or things like that. These things are just not defined at the Big Bang. One tiny moment after the Big Bang, 10 to the minus some seconds, then you can talk about the whole universe, and it might already be infinitely big then, and there's some finite number of particles per cubic centimeter, etc. Okay, that's one thing. But the other thing is more straightforward. You're saying if expansion beats gravity the very first moment, it seems like expansion would always beat gravity. Well, no, because, there's equations here, and you have to solve the equations. There are two things going on. The universe is expanding. Particles moving away from each other, but they're exerting a gravitational force on each other, and there's a competition between those two things. So which one wins depends on the magnitude of the expansion rate, right? It is exactly like taking a ball and throwing it up in the air, right? If I throw a baseball up into the air, as it goes up, the gravitational force on it is getting weaker, because its distance from the center of the Earth is increasing. So the force of gravity on the ball is getting weaker and weaker as that ball goes up. And yet, most of the time, when I throw a ball up into the air, it comes down. Because even though the gravitational force is getting weaker as the ball moves up and further away from the Earth, it's only getting weaker a little bit, and its velocity is decreasing noticeably, so it just comes back. If I threw it at the escape velocity of the Earth, or greater, then its gravitational force, gravitational pull, would get weaker sufficiently fast compared to its velocity that it would escape to infinity. The expanding universe is exactly the same thing. If the universe is expanding really fast enough, then it will expand forever. That's an open universe, and you will never have enough time to make structure. If it's expanding slowly, it could actually not just form structure, but it would turn around and recollapse in a very small period of time. So for whatever reasons, and that's a whole nother discussion, but the real universe had a balance, or a near balance, between the gravitational pull of particles and the expansion rate of the universe, so that the universe expands for a very, very long time, but there is enough time to form structure. Anonymous says, I can understand many physical constants as we accidentally have two units to measure one thing. Seconds and meters for measuring space-time intervals, kelvins and joules for measuring energy per particle. But I don't have a good physical intuition for what Planck's constant means. Momentum is really wave number, energy is really frequency. Well, so I think that you have outsmarted yourself, Anonymous, by understanding physical constants as accidentally having two units to measure one thing. So for space and time, for example, you're saying that we can use the speed of light, c, to convert between seconds and meters, which is true. But they're not the same thing. Space is not the same thing as time. There's an arrow of time. There's not an arrow of space, right? There's only one dimension of time. There are three dimensions of space. They're related. They're both different parts of space-time, but they're not the same thing. So I think that the general strategy of trying to understand physical constants as measuring the same thing using different units is not going to be a good one. Planck's constant is not that. Newton's constant of gravity is not that. The mass of the electron is not that. These are not conversion factors between different but equivalent physical quantities. So it's not that energy is really frequency. You're thinking of the famous formula E equals hf, I guess if you want to use English letters, Roman letters. F is the frequency of a wave, h is Planck's constant, E is the energy of a quantum of that wave. But that doesn't mean that energy is frequency. It just means that the energy of a quantum of a wave at that frequency is given by that number. So different physical constants do different physical things. And I think you're trying to squeeze them into too tiny of a box. Chris says, how have your colleagues reacted to the amount of public communication work that you do? Well, my colleagues are a heterogeneous lot. They've reacted in many different ways. There's absolutely people who don't like it. They will rarely say they don't like it out loud because they like the idea of public understanding of science. But then at the same time, for the people who actually do efforts in that direction, they will disparage them because they're not spending their time doing research, and what they value is the research output. That's a very real thing. And it goes the other way too. There are people who love the fact that there is public outreach. What's interesting, what you might not guess, is that even within physicists, different, like if you do a lot of different things, you write physics papers, you do outreach, you write books, you whatever, different people know about some subset of what you do, right? So there are people who, are only vaguely aware that I do outreach or public communication or write books or anything like that, but they've read my physics papers. There are other physicists who have no idea that I've written any papers in the last few years, right? They think I'm just writing books. It takes, 2 seconds on my webpage to figure out that I'm actually doing both. But if you're aware of one and not the other, then that's a perfectly natural thing. So, I think overall, I've written plenty about this on my blog. For example, there was a semi-infamous blog post I wrote called How to Get Tenure at a Major Research University. And the point being that at those very tiny subset of universities known as major research universities, what they care about is the research. And at best, what they will say is, well, if you're good at teaching or outreach or whatever, or organizing or community service, that will count a little bit, but it won't really help you very much. It's not most important. What's most important is research. But that's false. They're not telling you the truth there. They might even be lying to themselves. I don't know. But the point is, if you do any of those things, secretly they will be thinking, well, they could have been doing research during that time. And it's kind of an interesting, weird phenomenon because if you, play guitar, okay, if that's a hobby that you have, no one cares about that. Go ahead and play guitar. But if you write books about physics, they care about that. That it counts against you. And you might say, well, why would playing guitar not count against you, but writing physics books count against you? In their minds, they're thinking that the time and effort that you spent writing a physics book could have been used doing physics research. Whereas the guitar playing time is just a separate category, so that doesn't count against you. So the system is biased against you, but individual people react in a wide variety of ways, as you would expect individual people to do. Chris Rogers says, is there a parallel universe where the Nazis won World War II? That seems like a shame. So it's a short question, but I already have 3 things I want to say in response to this. One is, who cares if it seems like a shame? I'm sure that you're being somewhat humorous here, but of course we want to find out what is true, not what we want to be true. So whether it's a shame or not is irrelevant, whether it's true, as I'm sure you already know. More importantly, number 2, if there's a parallel universe where the Nazis won World War II, then there's a parallel universe where World War II didn't even happen. And that would be awesome, right? I guess. But most importantly, number three, if the parallel universes we're talking about here are Everettian universes, are different branches of the wave function of the universe, then it's true that there are many different branches where many different things happen. Not everything happens. Things happen that have some non-zero amplitude in the wave function of the universe, which is certainly not everything that you can imagine. But not all universes are created equally. And this is the absolutely crucial thing that I've said before, I'll say again, will always keep saying. You can't just assign sort of an equal amount of oomph or weight to every branch of the Everettian multiverse. Number one, it's not what the theory says. Number two, it wouldn't work empirically. You would get that probability rule wrong that we were talking about. The thick universes, the universes that have a lot of amplitude associated with them, count more. And typically, and this is something which is hard to work out quantitatively, but we can sort of try to get a feeling intuitively for what's going on. When you're talking about big human events, these are mostly classical. And what that means is that there is a way that things can happen where almost all of the amplitude ends up, right? When you throw a baseball, there's some probability that it's going to just zoom off into space and never come back. But mostly it's going to follow its classical trajectory. Both universes are real, but one is overwhelmingly bigger and more important than the other ones. So when you think about universes where the Nazis won World War II or World War II didn't happen, it's overwhelmingly likely that these universes have very, 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 very tiny amplitudes in them. So don't worry about them, honestly. Either don't believe Everettian quantum mechanics or don't worry about these universes. Those are your two intellectually consistent choices. If you think that Everett is right and explains probabilities and things like that, then you should assign smaller intellectual weight to the branches of the wave function of the universe that have a much smaller amplitude. Brendan Hall says, what did you think about Barack Obama's presidency? Well, it's a complicated thing. A presidency is a very big thing. Overall, I was positive about it, positively disposed toward it. There's a couple of complicating factors. Number one is that he started off with a very, very bad hand being dealt with a gigantic financial crisis and a lot of not to mention foreign policy crises, etc. So a lot of the work was necessarily preventing collapse rather than building new wonderful things. And number two, I think that as talented as Obama was, he was young, right? That was a legitimate worry about him when he ran for president. He didn't have the experience that some other people had. And I think that showed up in his being too optimistic about how he could get Congress to work with him and things like that. So he accomplished less in that sense than he would have. But overall, my feelings were good. And look, any president who was president for 8 years, or for that matter, even 4 years, does literally thousands of things. And so, of course, you can pick out things, and I could pick out things that Obama did that I really, really disagree with very strongly. But what has to count is the average weight. Likewise, when you have someone who you like as president, you can ignore the bad things and just count the good things because there's just so many things going on. I think that if you're going to try to, which I'm not doing right now, by the way, but if you were going to try to do a comprehensive and fair evaluation of someone's presidency, you can't just pick out the best and worst things. You have to pick out everything. And you also have to be counterfactual. Like if this person weren't there and there was someone else in the White House, then how things would things have been in that case? And I can imagine it being much, much worse. Let's put it that way. John Farr says, can you speak a bit about the virus and the vaccine? Is the virus research gone wrong? Is Bill Gates the mastermind? So much misinformation, and it would be nice to hear your voice of reason on this one. So I'm not sure exactly what the implication of this question is with the virus research gone wrong and Bill Gates the mastermind. No, I don't think the virus research has gone wrong at all. I think it's been a brilliant success story. Bill Gates has nothing to do with it, roughly speaking. I think that when future historians write about this era and they say, oh yeah, that was the time when they had a major pandemic that killed hundreds and thousands of millions of people, and then they quickly discovered a vaccine that would basically wipe it out, but people decided not to take it. Why were they such idiots? I can't even imagine what they will be thinking about what the rationalizations were. It's okay to say, well, there's a vaccine, it's new, I wonder if it works. But there's not really any disagreement amongst credentialed experts about the vaccine. It's really, really good. In fact, the overwhelming majority of scientific studies have been along the lines of the vaccine is even better than we thought it was going to be. So it's okay to be worried about that, but if you actually read what sensible people are saying, it's pretty unanimous. And especially compared to the alternative of not taking the vaccine, you're seeing now that a overwhelmingly non-representative fraction of people who are in the hospital, especially with very serious symptoms, are the unvaccinated ones. People who are vaccinated don't get the virus with nearly the same rate as vaccinated people do, as unvaccinated people do. And when they get it, the disease is not as bad. That may or may not continue to be the case as new variants emerge, etc. But right now, this is not a hard question, I'm afraid. It's pretty obvious. DMI says, what do you mean by exist? Would you say that numbers exist? If you would say that logic exists within language, what do you mean by logic? Well, I do think that this is a good question to which I can't give you a full answer. I cannot give you an answer that is completely satisfactory because I haven't worked out for myself what I think the answer to this question should be. I think it's a tricky question because I think that different things can exist in different senses. I think the most down-to-earth sense of existence should really be reserved for physical reality. That's what exists. And of course, different aspects of physical reality exist also. So I don't think that numbers exist or logic exists in the same way that physical reality exists. But there's some reality, some oomph, some power, some non-arbitrariness to numbers and logic that is very important. I just don't think it should be given the same label, existence, in the same way that the physical world exists. I'm a reality realist, as I like to say. Leah Reichwald says, what are your preferred sources of information for news and informing your worldview more generally? So again, I don't think this is a hard question. I think that most straightforward mainstream news media mostly do a good job at reporting facts. Not a perfect job by all means. As someone who has, read stories in news media about science things that I know very well, I know perfectly well that media can get things wrong, okay? But in basic things that are happening in the world, like there was, a building that fell down, I believe what the mainstream media says about those things. I certainly don't believe conspiracy theories where the media is trying to mislead you. There's a set of very real critiques of the mainstream media dealing not with what it factually reports, but what it chooses to report and not report. And number two, the spin that it puts on reporting things and not reporting things. But that's a very long, complicated, non-trivial conversation. If you think you have simple answers to those, then I'm already going to disagree with you. I think it's complicated. But so in addition to that, I think that it's good because, even mainstream media has its blind spots and its biases. It's good to have a variety. So for what I do for that, and again, nothing very profound about my own personal technique, but that's where I find social media very useful. Following a lot of different accounts on social media from a wide spectrum of different points of view and different interests will help point you to things that might not have appeared in the mainstream media. And you should always be a little bit more skeptical of those, but you can, again, get a feeling for how credible they are, etc. So I get sort of most of my news from conventional sources, but then I try to keep a lot of people I trust in the social media feed so that I can get pointed to things that I would not necessarily have come across if I were just reading the New York Times or the Wall Street Journal or whatever it was. Adrian says, around 10 years ago, you wrote an illuminating blog post about how energy is not necessarily conserved in cosmology. Are there ways to harness usable energy from that, at least in principle? Roughly speaking, that's probably a complicated question, but roughly speaking, the answer is no. There could always be loopholes that I haven't thought of here, but the point is that energy is not conserved in cosmology, at least the energy of stuff is not conserved in cosmology, because the existence of general relativity, where space-time is dynamical and responds to matter and energy, means that the total amount of energy, rather than just being a constant, obeys a relationship with the curvature of space-time. Okay, so space-time expanding or contracting or doing other things can change the amount of energy in matter and radiation. And to be useful, you say usable energy. If you're here on Earth, space-time isn't changing that much, right? So in the approximation where space-time is static, which is a really good approximation here on Earth, then energy is conserved. So I don't see any useful way to get anything from that subtlety of general relativity. Okay, I'm going to group two questions together because they're about the matter-antimatter asymmetry in the universe. Clyde Schechter says there are two difficult to explain asymmetries in physics that I struggle with understanding. One is the macroscopic existence of an arrow of time, when the laws of physics on the microscale are invariant under time reversal. The other is the predominance of matter over antimatter. Again, nothing in the micro laws of physics calls for this. My question is whether these two asymmetries are related in some deep way. And the other is from Sam Cartford, who says, question on baryogenesis. I've heard two potential theories explained, one being there is an asymmetry between matter and antimatter in the physics of the early universe, and the second being that we can only exist in a universe with this discrepancy, so we might just exist in a statistical anomaly, so something like the anthropic principle. So to Sam's question, that second possibility, that there's just a statistical anomaly, no one believes that. No credible person believes that. Number one, I don't know where the statistical anomaly would come from, but number two, whenever you run these anthropic arguments, the correct thing to do is to say there's a distribution of possible configurations of stuff, environments, situations in the universe, and living creatures will only exist in those particular configurations where life is possible, okay? So to do this at all, there's a selection effect. You're only observing those circumstances under which life can exist and observers can be found. But you need a distribution. You need to know how many of one kind of situations there are versus how many of another kind of situations there are. And therefore, when you need some kind of fluctuation to let life exist, generally the anthropic principle would predict, absent any other mechanism, that the fluctuation will be as small as it needs to be to get life to exist. Whereas in our observable universe, there's 100 billion galaxies or 1 trillion galaxies, and they're all matter. They're not all antimatter. That would be a much, 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 much bigger fluctuation than you would need for life to exist. So it could be that the asymmetry between matter and antimatter is just baked into the initial conditions of the universe, but it's much more likely and much more popular to think that there is some, like you say, asymmetry in the dynamics of matter and antimatter that created that difference. So Clyde is asking whether that asymmetry could have anything to do with the arrow of time. Not that I know of. There is the arrow of time in the sense of irreversible processes existing in the universe is because entropy is increasing. To get an asymmetry in matter versus antimatter, you need to violate what is called time reversal invariance, which is not quite the same thing. Time reversal invariance can be violated and is violated by the fundamental laws of physics as we understand them without violating reversibility. So things can go one way, but still have the property that you know exactly where they came from. So remember, the ice cube melting into a glass of water, the irreversibility comes from the fact that given the final state, a cool glass of water, you don't know where it came from. You don't know whether it came from a cool glass of water 10 minutes ago or whether it was a warm glass of water with an ice cube in it. Whereas in particle physics, there is T violation, T being the time reversal operator, but everything is still reversible. It's unitary evolution, smooth reversible evolution from one state to another. But that is all you need, or that is one of the things you need. You need that kind of time reversal violation in order to get a baryon asymmetry, more baryons than antibaryons. As far as I know, you do also need, as Andrei Sakharov pointed this out back in the 60s, you also need a departure from thermal equilibrium, which does rely on the arrow of time. So I guess the right thing to say is that getting a baryon asymmetry requires an arrow of time, but an arrow of time does not require baryon asymmetry or any of the other ingredients for getting a baryon asymmetry. So if anything, the connection goes one way, but not the other. Kathy Seeger says, I've read that in June 2021, British astronomer Alexia Lopez and team discovered a so-called giant arc, a structure of galaxies spanning 3.3 billion light years. It was said that this wouldn't go along with the cosmological principle that matter on a large scale is evenly distributed throughout the universe. Is there an explanation that could align cosmic inflation and unevenly distributed matter? So, two things here. One is I haven't read the paper. I haven't read the specific example, so I can't comment on the giant arc or whatever it is. But number two, there's essentially zero chance that the distribution of matter in the universe is flagrantly at violation with the cosmological principle that matter is evenly distributed. The reason why is because we have the cosmic microwave background, right? The cosmic microwave background is much more precise and easy to measure than the distribution of galaxies. And it's super duper isotropic. It looks the same in every direction. If matter through the universe was distributed very non-uniformly, you would know because the microwave background would reflect that, even if it just through gravitational lensing, etc. So I'm 99.999% confident that any distribution that you find in galaxies or collections of galaxies will ultimately be compatible with more or less cosmological homogeneity on very large scales. It's not perfect, right? It's a good approximation, but it's a very good approximation. Okay, I'm going to group two questions together. Ulrich Scheibe says, the Marvel Cinematic Universe Loki series, as well as upcoming Spider-Man and Doctor Strange movies, are diving headfirst into the multiverse. The explanation for how this fictional multiverse works was explained to Loki at some point, and the broader lines seem to be heavily influenced by many worlds theory. You mentioned once that you had a small part to play in Avengers Endgame. Have you been consulted again? If so, do elaborate on your involvement if you can. And Rob Kraft says, I recently reread the novel Dune by Frank Herbert in preparation for the upcoming movie. This is the first time I've read it since becoming familiar with many worlds. It occurred to me that Herbert's description of Paul Atreides' ability to see the future and possible timelines aligns with the Everettian idea of the branching of the universe. Do you think Herbert, who published Dune in 1965, could have known the Everettian interpretation and used that as the basis for his explanation of Paul's ability to see the future? So I'm grouping these together for the obvious reasons that they're connecting storytelling versions of the multiverse idea and asking if there's a connection with the Everettian quantum mechanical version. And I want to emphasize that if there is any connection, it's a very, very tenuous one. These are stories. These are, in fact, fantasy stories, even though they're gussied up in some science fiction-y elements. The authors just make up the story, the rules of the game, for dramatic purposes, okay? Maybe they were inspired a little bit by Everett and quantum mechanics or by the cosmological multiverse, etc. I don't know. But they don't need to be. You could easily come up with these ideas without that particular inspiration. And certainly the actual ways in which they implement the multiverses in both cases are nothing to do with Everettian quantum mechanics. Now, I can reveal that when I was talking to the folks in Avengers, I got some advice in there that was taken about time travel, but I had, a more elaborate scheme for fixing the whole universe. So my idea was that there really were branching timelines. Remember, when the Hulk goes back to talk to the Ancient One, played by Tilda Swinton, and she gives him a spiel about the one timeline and the other timelines, and that is elaborated on in Loki, which is a great series, by the way, if you haven't seen it. So the metaphor that is kind of used in the Marvel Cinematic Multiverse is pruning the other timelines, right? Getting rid of them somehow. So my idea was that would be terrible because that's literally committing genocide, right? You're literally ending the lives of trillions and trillions of people living in this timeline, and that should be bad. That should be considered to be immoral, if anything is. And therefore, a better thing to do would be to re-merge the timelines. Again, this can't happen in the real world. I made it up. But I thought it'd be interesting to imagine that the difficult task that they faced was to sort of line up what was physically happening in all the different branches of the multiverse so that things once again came together to make one big branch. Therefore, you could sort of preserve a single timeline without literally committing genocide and killing a bunch of people. I think that was too conceptually complicated and subtle for them to go with, so they didn't. But still, there's a novel out there waiting to be written that has that idea in it. Tim Kennedy says, I've long been curious about the mass of the proton. I've been taught and can accept that it comes mostly from the binding energy of the quarks inside, but in a recent AMA you characterize the inside of the proton as a roiling soup of quarks that are appearing and disappearing, but with a constant instantaneous average of 3 quarks. I had convinced myself that having exactly 3 quarks constantly racing around at near light speed could result in a very large binding energy, but now I am confused again. Maybe I should not be imagining the mass of the proton as something resulting from classical mechanics. So once again, a lot going on in this question. First, I have no idea what I said in the last AMA. My short-term memory and my long-term memory are both very bad, so forget what I said. I certainly would not want to characterize the inside of a proton as a roiling soup of quarks appearing and disappearing. What I really like to emphasize over and over again is that in quantum field theory, the state of something like a proton is static. There's nothing changing. There's nothing roiling. There's nothing appearing and disappearing inside a proton. We speak about it using a sloppy language of virtual particles appearing and disappearing, but what really is there is just a fixed, constant, static quantum field configuration. If you force yourself to interpret this quantum field configuration as a collection of particles, I'm not forcing you to do that, but if you just insist, and you imagine drawing Feynman diagrams representing what's going on, the Feynman diagrams would look like a bunch of particles popping in and out of existence. But the sum of all of them would be a static, unchanging field configuration. So quantum field theory really matters here. That's one thing. The other thing is the extra energy. So the point of this question is that if you calculate the mass of a lone, all by itself quark, okay, that's a tricky thing to define because there's no such thing as an all by itself quark. Quarks are confined inside bigger particles, but you can do it. You can do something like it. And the masses of the 3 particles that go, the 3 quarks that go in to make a proton are less by a lot than the mass of the proton, okay? So the mass of the proton doesn't come from the mass of the quarks. It comes from the energy contained in the gluon field, in the strong interaction analog of the electric and magnetic fields. So here's the way you should think about it. Imagine there was an electron. So forget about quarks because quarks are complicated. Take an electron. And imagine that you could turn off the electric field of the electron, okay? You can't, but imagine you could. And the electron has a mass then, all by itself. An uncharged electron has a certain mass. And now gradually turn back on the electric field. Well, it takes energy to turn on the electric field, to create that electric field out of nowhere. So E equals mc squared, the energy contained in a motionless particle, a particle at rest, is what we call the mass, divided by the speed times the speed of light squared is the energy. And so you have more mass. There's more energy and therefore more mass. There's a contribution to the mass of the particle from its electric field. And physicists argue about, renormalizing this and what counts as what, et cetera, et cetera. But the point is there's energy and therefore mass contained in the electric field as well as in the bare mass of the electron by itself. And one reason you know this picture works is because if you take an electron and a proton and you bring them together, they make hydrogen, and it's a stable configuration. It takes energy to remove the electron from the proton, and the reason why is because the electron's electric field has energy, the proton's electric field has energy, but when you bring them together at large distances, they cancel, and they have no energy. So there is less energy in the combination of electron and proton than there was in the separate electron plus the separate proton, because both of those guys had electric fields, which carry energy. And when you combine them, the electric field mostly cancels and the energy goes away. Exactly the same story is true for quarks in a proton. Now you have 3 quarks in the proton, 2 ups and a down. They're different colors. But if you took a quark all by itself, it would have a field, a gluon field, a quantum chromodynamic field, which is the quark equivalent, the strong interaction equivalent of the electric field around the electron, okay? The difference is, and this is the crucial difference that makes the strong interaction special, just like you take the mass of the electron and then add to it the energy from its electric field, you take the mass of the quark and then you add to it the energy from its quantum chromodynamic field, but that energy is infinite. If you had a lone quark all by itself, the energy in the gluon field around it would be infinitely big. However, if you have 3 quarks, all of different colors, then, just like the electron and the proton, the fields cancel out at infinity. So you get a finite energy remaining, a finite little remnant energy in the gluon fields of the 3 quarks that are combined together to make the proton. That's why you can't take a quark out of the proton, because it would require an infinite amount of energy to have a quark all by itself. But inside the quark, there's still some energy from the leftover quantum chromodynamic field, and it's from that energy that the proton gets its mass. The proton does not get its mass because the electrons or the quarks are moving. They're not moving. They're in their ground state. They're in their lowest energy states. It's from the quantum chromodynamic field that carries some energy, most of the energy, in the proton or likewise the neutron, etc. Okay, grouping 2 questions together. One is from P. Walder, who says, critical rationalists such as David Deutsch seem to suggest that induction cannot be a valid approach to gaining access to truth about reality. They also seem to suggest that Bayesianism is dressed up induction. Can you explain why you feel Bayesianism is a better approach to understanding the nature of reality than hard-to-vary explanations that are advocated by critical rationalists? And Jeff B. says, are there any convictions that you hold about the universe that are not based in scientific evidence but just feel right to you? Okay, these 2 questions might seem different, but I'm going to relate them. The point being, I'm not very familiar with Deutsch's argument as to why Bayesianism doesn't work and something else does work. He's a more Popperian, I know that. But I haven't read his stuff very carefully. I'm only very vaguely familiar with it, so I can't comment on what David Deutsch is saying. So I'm not going to say it yes or no. I can try to justify what I want to say, because what I want to say is the opposite of saying Bayesianism is dressed up induction. I want to say that Popperianism, falsificationism, is dressed down Bayesianism. So to say that, you have to be clear about what you mean by Bayesianism, because Bayesianism comes in 2 parts. One is Bayes' rule, right? The formula, or Bayes' theorem, or Bayes' law, or whatever you want to call it. That's a theorem. That's a mathematical result. It's just a statement about how probability works. If you're dealing with a set of quantities that obey the axioms of probability, then Bayes' rule is just true for those quantities, those probabilities. So there's no option there. There's no other way to do it. The part where things become a little bit more potentially controversial is not the formalism of Bayes' rule, but the meaning you attach to those probabilities, okay? Where you go from just applying Bayes' rule to sort of doing Bayesian reasoning is in the step where you say, okay, to every proposition I think of, I attach a prior. I give a prior credence or a prior probability that that is true. And then I learn more about the world by looking at the world, right? Doing experiments, gathering data, calculating the likelihood that if these propositions that I'm thinking about were true, I would have collected that data, and then using Bayes' law to update my credences from priors to posteriors. So the tricky thing that not everyone agrees with is the idea that we get reasoning off the ground by starting with a collection of priors about different things. It's a very subjective way of doing probabilities. You're thinking of probabilities as degrees of belief, as credences, rather than as frequencies of things happening. And to a Bayesian like myself, it's hard to imagine doing it any other way. Like if you say, what is the probability that it will rain tomorrow here where I am in Boston? It's pretty high because we're at the remnants of a hurricane coming. But it's going to rain or it's not. Like there's no frequency involved there, right? It's a degree of belief. It's the best prediction I can make given the information I get. So to Bayesians, this is just how to work. And there's really no other alternative. But a lot of people react against the idea that that probabilities should be something fundamentally subjective. Different people can have different priors, and that bugs them. Now, that's not what is bugging, I think, David Deutsch, etc. The problem of induction, a well-known problem that David Hume and other people talked about a lot about, is you can't prove things with metaphysical certainty just by observing a lot of instances, right? Can you prove that all swans are white? Well, you observe every single swan, and they're all white. Okay, have you proven it? Well, unless you've literally seen every single possible swan, it is always possible that tomorrow you'll see a black swan. And therefore, you haven't proven anything, okay? So I would say that Bayesianism is not dressed up induction. Bayesianism is the fix to that problem. Because sure, you're not proving with metaphysical certainty that all swans are white, but you start with a prior that either swans are white all the time, or there's another prior on the proposition that some swans are white and some are black. You used those theories to make predictions for what the color of the next swan you're going to see is. You update your credences as you get more data in. But the critical thing is your credences never go to zero. Right? You can see a billion white swans in a row. You still have some non-zero credence that some swans are black, because if some swans were black, but only 1 out of a billion, there would be some probability, some likelihood that that's what you would have seen. So you don't run into this problem that induction runs into, because you're not trying to prove things with metaphysical certainty. You're just updating your credences as you get more information. Now, the Popperian falsification way of doing things, and again, I haven't read Karl Popper in any detail either, so you Popperians out there, don't get mad at me. I'm discussing not really what Popper said, but sort of the cartoon Popper that a lot of scientists carry around with them. This idea is that you list every possible thing that could be true, and you don't assign prior probabilities to them, credences to them. You just say it could be true, or it either is true or it isn't, I don't know yet. And then you do experiments, you collect data, and you figure out, oh, this piece of data is incompatible with that theory, therefore it's false. It's been falsified. And so rather than having a large list of propositions and assigning credences to them, you have a large, maybe even larger list of propositions, and some of them have been falsified and some of them have been not. And that's it. That's what you're allowed to say. If you haven't falsified anything, then it's not yet falsified. That's all you're allowed to say. To me, that's just a crude approximation to being a good Bayesian, okay? Because in reality, we don't assign equal prior credences to every possible proposition. And it would be crazy, I think, to do that. No one does it. No one should do it. Why pretend that that's what we're doing? Or even failing. I guess no one would say you should apply equal credences, but some people would say just don't apply credences. I think that also fails. I think you have to apply credences. They might be implicit. You might not be very above board about it, but implicitly you're doing that all the time. And that's why I'm grouping this question with Jeff's question. Are there any convictions that are not based in scientific evidence that just feel right to me? So the short answer is no. I mean, the principled answer is no. You know, I do have beliefs, degrees of belief, credences for how the universe works, but I'm willing to update them, okay? And it's, you know, to say they're not based in scientific evidence is hard to exactly countenance, because these beliefs came from somewhere, usually from observing other things about the world and saying, well, you know, this sort of extrapolates beyond what I've seen to other things that I think are right. So mostly, I don't have any convictions about the universe that are not based in scientific evidence. I do have prior probabilities. The one counterexample or loophole to that is that there are some propositions which, if they were true, science itself would not be possible, right? If I were being taunted by an evil demon and all of my sense data were completely unrelated to the reality of the world, then I'm not able to do science at all, right? Or if I were a Boltzmann brain that just fluctuated into existence. So these are self-undermining or cognitively unstable beliefs about the world. And so I have a prior probability that is essentially zero that those are true. It can't even be exactly zero because maybe the demon walks through the door and says, "Ha, see, I've been fooling you this whole time." You never know. But you keep that probability so low to begin with that you don't take it seriously unless you're forced into it later on. Brian F. Carpenter says, "I've been trying to find out the orientation of the Milky Way galaxy in relation to the origin of the universe or Big Bang event, and more broadly, the orientation of space-time and general relativity. In other words, if space-time is like the fabric of a trampoline, how do we know on which plane it's stretched and why?" So I have to unask this question, Brian, because space-time is not like the fabric of a trampoline. You know, when we visualize, again, I already said bad things about our tendency to need to visualize things earlier on, but some things are not visualizable. Space-time is four-dimensional. It's not two-dimensional, like a trampoline. A trampoline or a sheet of rubber or whatever has the feature that it is embedded in a bigger space. If you treat the trampoline as two-dimensional, it's embedded in three-dimensional space. And therefore, if you take the trampoline analogy too seriously, you begin to think that space-time is embedded in something, but it's not. So there's no such thing as the orientation of space-time. With respect to what would it be oriented? I don't even know what it could possibly be oriented with. So I would just undo the premises of your questions. There is a more down-to-earth question, that you get to, which is like you have a bunch of galaxies, a bunch of stars, a bunch of solar systems, and they have angular momentum, right? They're spinning. So there's some plane in which things are aligned. And is there some universal lining up of these planes? Like, do different galaxies still orbit in the same direction? And the answer there, as far as anyone knows, is no. People have looked at that a little bit, not very carefully, but we're so sort of convinced theoretically that it would be weird for that to be true, that it's not a high priority for people to collect data and look at it. When they have, they found no evidence that there is any general alignment of different things in the universe. Brian Owenson says, "You recently tweeted that most of the mass in your body is made of particles containing 48 quarks. You must be referring to an oxygen atom. Are there any interesting questions that are better addressed by thinking of an oxygen nucleus as a pool of 48 quarks, as opposed to thinking about the nucleus as a pool of separate protons and neutrons?" So there's a couple things going on. Just to be strictly clear, you say oxygen atom, but what you mean is oxygen nucleus. It's the nucleus that is made up of 48 quarks. The reason why I made that quip on Twitter is because people were, as they occasionally do, getting excited about tetraquarks or other collections of new collections, previously undiscovered collections of quarks that you can find at Large Hadron Collider or wherever. And it's great. This is important science. Don't get me wrong. It's important to do this, to learn about quarks and QCD and the strong interactions and how they fit together. But I worry that people are getting excited just because there's more than 3 quarks in this particle, okay? We have plenty of particles with more than 3 quarks in them. Every atomic nucleus is a particle with more than 3 quarks in them. And so that's why I picked oxygen, because most of your body mass is in the form of oxygen nuclei. The point being that how do you define particle? There's 2 choices. One is you say, only the elementary particles count, in which case it's only quarks that count. Protons and neutrons do not count as particles under that definition. The other definition you could use, which is also perfectly good, is a bound collection of particles, of fundamental particles, can be counted as a composite particle. In that case, mesons and baryons, like pions and protons and neutrons, those are all composite particles. Perfectly good definition also. But under that definition, atomic nuclei are composite particles. So you say, are there conditions under which you should think of an oxygen nucleus as 48 quarks rather than separate protons and neutrons? Yeah, all of the conditions. This is sort of a secret of nuclear physics that does not become clear when you look at little cartoon images of nuclei. Because when you draw cartoon images of, let's say, a hydrogen nucleus, sorry, hydrogen is not a good example, helium, 2 protons and 2 neutrons, you tend to draw separate protons and neutrons. But that's not what the nucleus looks like. It's just a spherical blob. And the spherical blob has all of the quarks and neutrons arranged in it, not exactly equally because there's the Pauli exclusion principle, but they're not confined separately to protons and neutrons, which then combine into nuclei. They're all in the nucleus. That's how they have names for like the nuclear drop model and things like that, the bag model. But you shouldn't think of protons and neutrons in a nucleus as having separate identities anymore. That's all just a sea of quarks. David Gotti says, priority question. My son is about to start a master's program in physics and would like to get a PhD after that. Much of his undergraduate work was in astronomy and physics, influenced by his key professor's work on galaxies, and he made poster session presentations at the annual American Astronomical Society conference. However, he is open to other fields within physics he has not been strongly introduced to yet. Can you discuss and give advice for him how to use his master's work to best set himself up to be a strong PhD applicant, and how his loved ones can best support that? So it's a bit of an unusual question, actually, David, because most, in the United States anyway, which is where I'm familiar with what goes on, most people who get PhDs don't go from undergraduate to master's to PhD. They do go right from undergraduate program to PhD program. That's the much more common route to go. You pick up a master's along the way, like after 2 years, they just say, oh, yep, here's a master's degree, no big deal. But it's not a separate step. So it's perfectly okay to go to a master's program first, but I'm just saying it's not the common route. So I'm not as good at offering advice about what to do because it doesn't happen that often. In fact, what I would say is this. Roughly, who cares that he's getting a master's? What matters is he's going to be applying for PhD programs. So the question is not what should you do in your master's program to prepare you. Your question is just how to be the best possible applicant to a PhD program, whether or not you have a master's degree. When you apply to PhD programs, again, I can only speak for the US because different countries are very different. Usually, you indicate a preference for a group to be a part of. So you'll have a department, physics department, right? But there'll be different groups within the department. Theoretical particle physics, experimental particle physics, theoretical astrophysics, observational astronomy, theoretical condensed matter physics, biophysics, etc., right? There are individual groups, and there are different faculty members associated with those groups. You might think that either you apply to the department or you very specifically say who you want your PhD advisor to be, but neither one is true. You typically say, I would like to be in this group, and then you get there, and when you're there and in the group, you sort of talk to the different faculty in the group and eventually settle on one as your advisor. So that's the sort of mindset that an applicant should have. They need to know what kind of group they want to be in. By the time you're entering grad school, you shouldn't be undecided about that anymore. You don't need to be decided about what exact research project you're going to do, or even deciding between like string theory and particle physics or something like that, things that are within the same group, okay? But you do need to decide what group you're going to be in, because different groups might have different numbers of people they can accept, different standards, different amount of funding available for new students, things like that. So it doesn't matter that much what research you did before you were a PhD student, whether it's undergraduate or master's. It's good that you've done research. Doing research is a good thing, but especially if you're going to do highly theoretical things in grad school. But even if not, it's generally understood that people will do different research in the PhD program than they did before. What's much more important is getting good letters of recommendation. Okay, that's the single most important. I should have said that first if I were front loading the important thing. The important thing to use that master's degree for is to have faculty members, ideally faculty members who will be known to people in the PhD programs they'll eventually apply to, get to know the student very, very well enough to really write a good letter of recommendation for them that can be explicit about why they're a strong applicant. It's also nice to get good GRE scores and grades and so forth. But if you really want to put your research time to work while you're a master's student, I see it all the time where people apply to grad school and no faculty member knows them well enough to write a good letter. And that's bad. That's a shame because that's really useful information for the admissions committee. So I guess the two things to do are, number one, get to know faculty members well enough they can write you good letters. Number 2, choose what group you want to be in when you apply to the PhD programs. And then you can hopefully find a group with many different faculty members in it. And once you're there, once your son is there, decide which of them might make a good advisor. Jesse Rimler says, worker-owned cooperatives are examples of extending democracy into the workplace. As a fan of democracy, are you interested in a similar extension of democracy into scientific institutions? I think roughly it's already there. It's too late. Science is not an autocracy. There's no pope or emperor of science. Science is run by scientists as a collective. And it's not very formal, right? You don't make elections, you don't vote on whether this theory is true or not, but individual scientists make up their mind and they vote with their feet. They vote with deciding what to do research on and what papers to write and who to hire and things like that. That's how they make the voting. And, they can be department chair or whatever, but who cares? Being a department chair means you decide who gets what office. It doesn't mean you decide what scientific results are true, okay? Science is very democratic. This is part of the wonder of how science works, is that ideas bubble up from the bottom, and you need to convince people that you're right, just like you do in a democracy. So I am a fan of exactly that. BK says, a lot of academics have dissected the show The Chair, which is on, where is The Chair on? Is it on Netflix or HBO? I forget. Anyway, they dissected it on Twitter down to the decor in the buildings, offices, etc., with reference to how realistic they look. What do you think of the representation of Caltech in films and TV shows such as The Big Bang Theory? So I have a small amusing anecdote to say about this. I've said it before, so apologies. Look, I only have a finite number of stories to tell, so those of you who listen to me too much are going to hear them all several times. My friend David Salzberg was the official science advisor on The Big Bang Theory. David is an experimental particle physicist at UCLA, and they really took the science advising seriously, way more than most science shows on cable TV do. Let's put it that way. What it means is that all the science dialogue and all of the equations on the whiteboards, etc., were from David, and he made absolutely sure they were accurate. Even if they were hypothesizing in plausible ways. So that's good, even though most people wouldn't really care, to be honest. But what was more interesting is before the show ever started, they were designing the sets, right? This is what you're asking about, how the places look. And they had these ideas, like, you would see a lab like you saw in the Avengers, right? Or, you see in any of these science fiction shows of very high-tech, glossy things with, gleaming lens flare and chrome and whatever. And then, so David Salzberg said, well, I'll take you on a tour of the labs in the physics department at UCLA. And the set designers were appalled. They're like, oh my God, this place is a dump. You're blocking your lasers with a piece of cardboard attached to a clothespin. This is not very high tech at all. Of course, because, you have a limited budget and you want to stretch the budget as far as you can. You don't spend your actual science dollars on a gleaming, all futuristic looking laboratory equipment. So that got reflected. If you look at the lab scenes in The Big Bang Theory, they're actually much more realistic than most other scenes. The other thing I can say along those lines is a slight faux pas on my part. I was once consulting on the TV show Bones. There was a murder mystery where the accused murderer was a theoretical physicist, played by Richard Schiff, famous as Toby from The West Wing. And so I got to write some of his dialogue, and in fact, some of the things he says have to do with entropy and the arrow of time, as you will see, and Robertson Walker cosmologies. And also write blackboards, which turned out to be an important plot point on the show, the blackboard. So if you see this show, if you want to Google the episode of Bones with Richard Schiff as a guest star, I forget what the title of the show was, but look, it's actually really extremely well done. Like, there's not a dry eye in the house at the end of this show, and your mistiness will be because of equations, believe it or not. I'm not going to give away more than that. But the point is, I walked onto the set. They had me visit, and I walked onto the set, and it's a typical Hollywood version of a professor's office, right? Like, big overstuffed leather chair, elaborate desk, all of these books that look like they're from 150 years ago. And I couldn't help myself. I'm like, yep, this is a very Hollywood-looking physicist's office. Real physicists' offices don't look like that. They're usually pretty Spartan affairs. The walls are often cinder block with a coat of paint. The books are not from 150 years ago. The chairs are not leather bound. Let's put it all that way. And I felt bad because the set designer was there, and they were hurt because they tried to do a good job, and they had no idea what a real physicist's office looked like. I mean, they're much smaller than what the TV show had also. So I at least said, well, let's put some more modern-looking books on here or something like that. Turns out to be hard to do because modern-looking books, you might need to get rights to show them on TV, et cetera, et cetera, et cetera. My third story, I don't know why I'm giving you all these stories, but my third story along those lines is on the TV show Fringe. I also consulted a little bit. And a friend of mine, Glenn Whitman, was one of the writers on the show. And so he asked me some questions about wormholes and things like that. And I gave him answers. And so as a reward, usually you don't get rewarded for this at all. You certainly don't get paid for any of this, that's for sure. So my reward was, he said, there's a scene in the script where someone is passing a book to someone else. We'll make it one of your books. We'll invent a book that you haven't written, but we'll say you wrote. So they invented a book called Cosmology by me, and John Noble's character says, "Have you stolen my copy of Carroll's Cosmology?" or something like that. And they have a book, like the set designer made a book with my name on the title, etc. And only afterward, this is before I had written most of my trade books, but only afterward did I say, I wrote a general relativity textbook. They could have just used that. I could have advertised my actual book instead of let them use a fake book. But no one said I was very smart about these things. My branding needs a little upgrading. What can I do? All right, that was a much longer question I answered than you needed for that question, but it's a good question. Paul Hess says, I believed you once mentioned that entanglement leads to or causes increased entropy. Can you explain this connection in a little more detail? As entropy always increases in the universe, does entanglement also increase in similar proportions? So I'm going to have to apologize because I do say things like that, and I try to be careful when I'm saying them, but there are nuances and details that get glossed over. There are different kinds of entropy. When I say that the entropy of the universe was low near the Big Bang and has been growing ever since, I really mean some kind of coarse-grained Ludwig Boltzmann kind of entropy, which means that there is a system, which is the universe, and there are many, many different microstates the system can be in. And we group together many of those microstates into a macrostate, count them, take the logarithm, and that's the entropy. That is a kind of entropy. There is another kind of entropy that exists in quantum mechanics that Boltzmann didn't know about it. Boltzmann didn't know about quantum mechanics. And this kind of entropy was invented by John von Neumann, and it's called either the von Neumann entropy or the entanglement entropy. And it's called entropy because it is entropy. It's a very similar conceptual thing. It has very similar looking equations, but it is a different thing, because entanglement exists in quantum mechanics and doesn't exist in classical mechanics. So the point is this. If you have a system where you know what macrostate it's in, okay, so you have a glass of water, a bunch of molecules in there, etc., but you don't know its microstate, entropy becomes useful because you can give a probability distribution to all the different possible microstates, right? You can say, well, I'm sure the system has some particular position and momentum and orientation of every single molecule, but I don't know what they are, so I'm going to talk about a probability distribution, okay? So the difference between knowing the exact microstate and just knowing the probability distribution, we call the former a pure state. It's an actual particular realization of the positions and velocities of all the molecules that Laplace's demon could work with. And we call a mixed state the idea there's a probability distribution over all the different possibilities. So the same thing is true in quantum mechanics. You can have a pure state, which is described by a wave function. You can also have a mixed state, which is described by some sort of probability distribution over different pure states. The difference that I'm finally getting to in quantum mechanics is when you have two systems and they are entangled with each other. Remember, the whole point of entanglement is that the two subsystems don't have a wave function all by themselves. There is only one wave function, the wave function of the universe. And if you just want to isolate your focus down onto two systems that are not entangled with the rest of the universe, but maybe with each other, then those two systems have a single composite wave function, okay? So if they're entangled with each other, then it is automatically true that even if you know the exact wave function of the complete two-system thing, two-subsystem system if you want, there is no single wave function for either of the constituents, okay? They're both automatically in a mixed state. You can describe, if it's A and B, if it's Alice and Bob, and they have their particles, and the particles are entangled, there is no wave function for Alice's particle, there's no wave function for Bob's particle, there's just a wave function for both. There's no state, there's no pure state for particle A or for particle B. But you can assign a mixed state to particle A and particle B. It's as if you didn't know that particle A was entangled, you would say that particle A is in a combination, not a superposition, but like a statistical mixture of different possible quantum states, and therefore it has an entropy. So the thing that is new is that in quantum mechanics, entanglement can lead to an entropy of subsystems, even if you know the exact state of the composite system as a whole. Having said all that, okay, that's the connection. Does entanglement increase as the universe goes on? Well, that's a complicated thing. I want to say roughly yes. I will not go into any more details than that, but the details are interesting, and I don't think we understand all of those details precisely. That's one of the reasons why I want to be vague here. Brad Malt says, in your podcast, Taking Aliens Seriously, Avi Loeb says that alien visitors may possess technologies so advanced that they would look like magic to us and miracles we cannot really understand. His logic is that our own technologies are evolving exponentially, so imagine what a civilization with a few 100,000 or millions of years could do. What is the coolest magic you could think that advanced civilizations might possess? And do you think this could be any of the following? The ability to connect with other branches of the multiverse, the ability to travel near the speed of light, the ability to travel backward or forward in time, or the ability to make use of dimensions greater than 4 that are currently accessible to us. Okay, so the reason why I wanted to answer this question is because this very interesting list of possibilities, actually you have 4 possibilities. Connecting with other branches of the multiverse, travel near the speed of light, travel backward or forward in time, make use of extra dimensions. These have very different statuses, these questions, okay, or these possibilities. So the ability to travel near the speed of light, absolutely, of course. We can do that with individual particles. We accelerate particles to near the speed of light. To accelerate a spaceship to near the speed of light is just a technology problem. Like that's very, very solvable. Whereas the ability to connect with other branches of the multiverse, we think is strictly impossible. There's nothing you can do in this branch of the multiverse to connect with any other branches. Likewise, when you travel backward or forward in time, well, backward and forward aren't created equal here. We travel forward in time all the time. I traveled forward in time yesterday by 24 hours, and here I am. You can even get there faster by moving near the speed of light. Whereas as far as we know, you just can't travel backward in time. Now, we don't know that for 100% sure. Check out the podcast I did with Kip Thorne for more on that. But it seems the smart way to bet is that you cannot travel backward in time. And for dimensions greater than 4, number one, we don't know whether they exist, okay? But number two, so this is a tricky one because if they do exist, it's not against the laws of physics to imagine using them somehow technologically, but it is almost against everything we know about how they would work. The energies that would be required to manipulate them are just enormous, and then they would relax back to their ordinary state. So even though it's not strictly speaking against the laws of physics, I see no way for advanced civilization to make use of extra dimensions in any practical way. Okay, 2 questions I'm going to group together. One is by Justin Bailey, who says, after listening to the podcast on Wu Wei with Edward Slingerland, I would really like to know what the flow state is like for you. Are equations pouring out on the page, paragraphs just appearing magically, and what does the flow for a cosmologist, quantum theorist like yourself feel like? And then Daniel Fox says, do you find concepts such as Wu Wei affect your approaches to creative thinking about theoretical physics? So very, very closely related questions. again, I'm not an expert on what really counts as that, but I think, many of us have had the experience that we've been in the zone in that flow state. And certainly that happens with theoretical physics. And actually, it's a really good question to ask what that means, right? If you're painting, or if you're playing a musical instrument, or if you're playing sports or something like that, or even if you're driving, it's very clear what you mean to say that you're in this flow state. You're sort of not consciously fretting about the details. It's just happening automatically. And we know as modern scientists that there are things going on in your brain, but those things are just not penetrating to the conscious cognitive system 2 part of your brain. They're all subconscious system 1 things going on. When it comes to physics, how do you even do physics subconsciously? That sounds like a very difficult thing to do. So no, equations do not pour out onto the page. That's just not how it works, really. I wish it worked like that. But there are, the equations are like the quintessential paradigmatic example of needing your system 2, needing your conscious cognition to kick in. But you can have states where it's sort of like, when you're puzzling over something and you go to sleep and then you wake up with the answer. There's the waking version of that. You can be so absorbed in a problem and sort of thinking about it in such a precognitive way that you make progress. And it's sort of quasi-visualizing, quasi-feeling, quasi-just letting everything go. The difference is that unlike playing a musical instrument, at the end of that process, you better have an equation, or at least an idea that leads to an equation, right? I mean, that's the difference. Something like theoretical physics is at its best a give and take, a dynamic back and forth between the sort of subconscious flow state and writing equations. Because once you write the equations, you say, all right, I need to integrate this expression. There's no being in the zone for doing an integral. You got to follow the steps. That's all I can say. Okay, Mark Smith says, if the branch of the wave function you're experiencing cannot interact with other branches, then what makes the actual existence of the other branches more likely than their non-existence? Well, again, I've said this before, I'll try to say it again in as compact and understandable way as possible. The existence of other branches is predicted by the Schrödinger equation. And the Schrödinger equation works. That's the short answer. The real question, the sort of question you should be asking is, why in the world and how in the world would you get rid of the other branches of the wave function? I mean, it's perfectly clear and unambiguous and uncontroversial that they are predicted by the Schrödinger equation, right? When we observe things in quantum mechanics, the measurement outcomes are not naively what you would predict by the Schrödinger equation, because the wave function appears to collapse. And Everett has a very clear story about decoherence and how that works. But Everett also implies that by taking the Schrödinger equation seriously at all times, the other branches are there, because that's what the Schrödinger equation says. So if you don't want to believe in them, the burden is on you to tell me why they're not there, to how you're going to change or add to or subtract from the Schrödinger equation to get rid of them. And that's exactly what people do. Spontaneous collapse models literally subtract branches from the predictions of the Schrödinger equation. Hidden variable models literally add pointers that say, this is the real branch. This is the one that actually exists, okay? Whereas Everett just says there's just what the Schrödinger equation says. And that's all we accept. Simon Carter says, what's the latest regarding your book writing? If memory... I'm hesitating because my British publisher I thought it was named Simon Carter for a second, but it's actually Sam Carter. So this is not secretly my publisher nudging me about my book writing. So sorry to confuse you about that, Simon. What's the latest regarding your book writing? If memory serves, you have put back the book on complexity and currently writing a big ideas book based on your YouTube videos and a quantum mechanics textbook. So yes, as I said, I think in the previous AMA, I shouldn't really say what books I'm working on ahead of time. It's bad karma or something like that, but it's too late now. The cat's out of the bag. So short answer is yes. Right now I'm splitting my book writing time between the biggest ideas in the universe, which will be a 3-book collection, Volume 1 Classical, Volume 2 Quantum, Volume 3 Complex, and the Quantum Mechanics textbook. So those are my priorities right now. I have many other books that will be written. Don't you worry, but I got to worry about a finite number of them at a time. Okay, grouping two questions together. One is from Ezra Parzabak, who says, do you think China, assuming they continue to rise in economic and scientific standing, will eventually build the next level particle collider? And one from Carlos Nunez, who says, what is your opinion on the rise of China? Should the U.S. use adversarial policies to try to impede them from achieving top superpower status? So the first question, I think the short answer is, yeah, I think it's quite likely that China will build the next level particle collider. I mean, they seem to want to do it. They have the money to do it. Why not? I mean, that's the nice thing about being an authoritarian dictatorship is if the dictator decides to do something, they can get things done. It's not necessarily good for everyone else in the country, but you can certainly get things done and you have the resources to do it. As to whether the U.S. should try to impede them using adversarial policies, I don't think that's really the right angle to take on asking the question, okay? Because it makes it sound like the bad thing is some other country being the top superpower. I don't think it's anything intrinsically bad about some other country than the United States being the top superpower. After all, if I lived in Iceland, I might complain about things the United States did, but I wouldn't feel that the United States was a threat to my status as a functioning democracy, being in Iceland or being in Canada or being wherever, right? Not every country needs to aspire to being the top superpower, and it's perfectly okay to not be the top superpower. The problem with China is not that it's potentially the top superpower, it's that it's an authoritarian dictatorship. It is a model of governance that is not nearly as good for the people living in it as democratic republicanism is. So that's what I worry about. I worry not that China is going to be more economically powerful, but that they will spread a political system to other countries that eventually results in a worse off life and set of rights for other people, as we're seeing in Hong Kong and elsewhere right now. So what should the United States do about it? I have no idea. I mean, that's the tricky thing. So given the reason why I'm sort of not exactly answering your question is, if the concern of the United States were just, we don't want anyone else to be the biggest economic superpower, then I can imagine certain adversarial policies to make that happen. But that's not what I care about. I care about the spread of democracy throughout the world and how to stop China from spreading totalitarianism throughout the world is a much trickier thing in my mind than just keeping up with them economically. So, the single best thing that the United States can do is not be an adversary to China, but to be a preferable role model, right? To be an example of a functioning democracy that other countries look up to. Sadly, we've been bad at that in recent years. So I would say forget about China, just get our own house in order. Be like that person we talked about earlier who is in a bad relationship and wondering how much work they should do to keep it going. Just worry about yourself first. Okay, Matt Hickman says, how does time reversal symmetry work for classical black holes, specifically a situation where a test particle just crosses the event horizon? So there's a short answer here because the classical black hole is itself not time reversal invariant. Okay, a classical black hole is much like a melting ice cube in a glass of water. The underlying laws of physics are time reversal invariant, but the black hole, the creation of the black hole increases entropy, just like the ice cube melting. So to complete that thought, there's no surprise then that the behavior of test particles in the vicinity of a black hole is not time symmetric. You can cross into the event horizon but not cross out of it. There is, just as there is for the ice cube, a solution to the equations of motion that is the time reverse. For the case of the ice cube, it would be a cool glass of water evolving into an ice cube in a warm glass of water. Unlikely, but it obeys the equations at the fundamental level. For a black hole, that would be a white hole. A white hole is just a black hole time reversed. And there, for a white hole, test particles can cross out of the event horizon, but not go back in. So the whole set of possibilities is completely symmetric. There are black holes where you can go in but not out. There are white holes where you can go out but not in. Matt Haberland says, in the past, your guest's audio quality has been consistently terrific, but recently there have been a few episodes in which the guest's audio quality is not as good. Did something procedural change? So I recognize that that's true, and no, nothing procedural has changed. It is a random fluctuation. It turns out that audio quality is a tricky, multivariable thing, and many things can go slightly wrong. I think you're right that there have been a few episodes recently where the quality was not as good. Trust me, I care a lot about getting the audio quality good, and I'm going to keep trying to make it as good as possible. But many things can get in the way. I do send my guests a microphone. Sometimes they don't want a microphone. Sometimes they have a microphone they think is just as good. That's fine. But what has happened, I think, just coincidentally, again, no systemic reason, recently is that people have had good microphones, but they've been in really echoey environments. As I say that, sitting in this apartment in Boston, I worry that I'm in a very echoey environment. So I hope this isn't very bad, but I think I can control it a little bit. But literally, I had a guest who was in the process of moving out of their office. I'm not going to say who. And so, there were no books or anything in the office. It was just an empty room. And we had literally tested the audio quality ahead of time, but in a different room. And they moved to an empty room before recording the podcast a week later. And then there was an echo. What can I do? So all I can say is I am learning more and more things that can go wrong with the audio quality, and hopefully this leads me to be better and better at preventing those things from going wrong. Liam Appleba says, in the episode with Brian Arthur about complexity economics, you asked if he was worried that his computational approach would be missing the deeper understanding you can get from an equation-based approach. What is it about equation-based approaches that gives it deeper understanding? If you mean intuitive level of understanding, surely you can get that from watching a simulation. So this is a good question. What I mean is just that an equation, in principle, in practice that can be hard, but in principle, an equation captures every possible simulation. Simulations are done one by one, right? You simulate this configuration and then that one, and you can try to span the space of all possibilities, and you realize, when I change this changes, okay. But an equation, in principle, contains all the possible things that can happen. It's a rule, right? So if I say that gravity is an inverse square law, I instantly know not only how planets move around the sun, but also how apples fall from trees. Whereas if I just do a bunch of simulations and see planets moving in ellipses, I say, oh, look, planets move in ellipses. Doesn't tell me about apples falling from trees. The equation instantly spreads to all these different situations. That's why I think that it can, in principle, once again, give you a more intuitive level of understanding. Niles Dar asks a priority question. I'd love your thoughts on my interpretation. The speed of light is the maximum processing power of the universe. Time moves forward constantly at the speed of light, bringing everything with it, but when an object approaches c, the universe struggles to facilitate its travel through time, causing dilation. Similarly, time dilation is experienced near a black hole because there is so much information being processed in such a condensed space. So I'm going to do something very dangerous here, Niles, and I'm going to try to give you my best answer. The reason why this is dangerous is because, it's always very possible that 50 years from now, we have a much deeper understanding of these things, and my answer turns out to be completely wrong. But my answer is, I don't like your interpretation. Sorry about that. For a couple of reasons. One is, you start by saying time moves forward constantly at c, but it doesn't. What does that mean? Time does not move at the speed of light. The speed of light is the speed at which light moves. Moving, in this sense, is traversing a certain amount of distance per unit time. That's why we measure the speed of light in something like meters per second. Time does not traverse distance, much less traversing distance in any particular amount of time. Time traverses time, so you can say how much time passes per unit time. The answer is always 1 second per second. I've said this before. I literally wrote that in my draft for the Biggest Ideas book just the other day. That's the rate at which time flows. 1 second per second. Always. There's literally no other rate at which it possibly could flow at, okay? So you say then, when an object approaches the speed of light, the universe struggles to facilitate its travel through time. Well, and this is why I hesitate. What I said about time is just true, but this is a little bit trickier because according to the theory of relativity, what you just said can't be right. Because you're saying that the universe struggles to facilitate its travel through time when an object approaches the speed of light, but in relativity, there's no such thing as approaching the speed of light as an absolute sense. There is the relative velocity of two different objects approaching the speed of light, but I can always switch to the rest frame of any object I want. So if one object is approaching the speed of light, I can just go to its rest frame and it's stationary in its rest frame. So the idea that the universe struggles to operate one way for one particle moving in one trajectory and a different rate for another particle moving on another one is incompatible with the spirit of relativity that says all such trajectories are created equal, okay? Now, maybe relativity will be superseded one day and things will be different, but that's what I would say is probably true right now. Cooper says, is there a sense in which entanglement can travel at different speeds through the environment? For example, inside Schrödinger's cat's box, the photons in gaseous matter quickly entangle, but then entanglement slowly propagates outward due to the solid, less interactive matter making up the walls. Is it true that you could cool a material down close to absolute zero to act as an entanglement shield? Really should have put this back up there in the entanglement question, but I think I've already answered it. Yes, there is a sense in which entanglement travels at different speeds through the environment. I guess the reason why I isolated the question is because for those of you who are interested, there is a mathematical result called the Lieb-Robinson bound. Elliott Lieb, L-I-E-B, Robinson, don't know their first name. They made a bound on the rate at which entanglement travels through a quantum system, and you can look that up. But it depends on the details. It depends on the materials that you're constructed of, the Hamiltonian or the interactions or whatever it is. But yes, and then you can take advantage of this different rate of entanglement spreading to shield things from becoming entanglement, and that's what you need to do if you build a quantum computer. Arthur C. Clarke, probably not their real name, says, could you elaborate on the difference between causality and determinism and what role entropy plays? Causality says that it implies... So I'm not quite sure what the language is saying here. Causality, arrow, implies that A causes B, but B does not cause A. Determinism, arrow, if you know the state of a system at any time and the laws of that system, you can calculate the state of that system at any other time, future or past. For example, Arthur continues, if I were to watch the movie of a perfectly elastic frictionless billiard table without holes, I wouldn't tell if the movie were being played forward or backwards. Therefore, I can't say with certainty what caused what to happen. However, I could calculate what the table looked like in every frame of the movie if I really wanted to. If that's right, is it still true for something more complex like scrambling eggs or stirring cream into coffee? So this is a complicated question. This is literally something I'm trying to write papers about right now. And the reason why it's complicated is because it's a question of emergence, once again. Determinism, in our current way of understanding the universe, so this is not a statement about every possible universe, but the real world, determinism is something that seems to be found at the micro level, right? Billiard balls, something like that, small numbers of moving pieces. At the emergent level, at higher levels, we're throwing away information, okay? That's what emergence is all about. There's many different microstates that look the same as far as macrostates are concerned. And therefore, it is often the case that the emergent theory is not deterministic. And there is an arrow of time, okay? So what I would say is there's no reason to ever use words like causality at the micro level. Causality, at least in the classical sense that Aristotle would have understood formal causes, etc., is a strictly macroscopic phenomenon, and it is a time-directed phenomenon. The causes never come after the effects. Whereas in microphysics, which Aristotle didn't know about at the time, we have reversibility, determinism, Laplace's demon, and so forth. So nothing is time-directed at the deterministic reversible microphysical level. Therefore, you shouldn't talk about causality. The interesting thing is to ask why, when you do coarse grain and go from the micro level to the macro level, you have something called causality that does play an important role and is a useful concept. And that's tricky, and I don't have a complete story to tell about it, but it will ultimately involve coarse graining and entropy and all sorts of interesting things that involve both philosophy and physics and computer science and stuff like that. Joshua Hillerup says, I know you aren't an expert in this, but from my understanding, you do talk to all sorts of experts. So I'm wondering, is there actually a way out of this pandemic? Given things like the Delta variant reinfecting people over and over again and new strains developing all the time, are we ever going to be able to live in a society that can open up again without sending massive numbers of people to the hospital or dying? So I'm not an expert, so no one should take my opinion about this seriously. You should listen to the experts. But I'm a human being and I do think about these things. These are important questions, right? I think that the most obvious long-term situation to be in, and it's far from completely obvious, but like the first thing you would guess is that the coronavirus, the novel coronavirus, that as we used to call it, SARS-CoV-19, is going to be like the flu, but worse. So the flu is a set of viruses, a wide variety of different kinds of viruses, that mutate, and so there's different kinds of flu every year, and thousands of people die every year. And there are shots you can get, and some people get them, and some people don't. And the number of people who die every year is sort of just small enough that we don't really go crazy about it, okay? The number of people dying from COVID is much larger than that. And I don't think we would put up with it if, 500,000 people died in the United States every year going forward as a rule. Like that would be that would be bad, and we would sort of not put up with it in the way that we put up with the flu. But you can imagine a sort of quasi-equilibrium where we fight it, but not very effectively. So many people get vaccinated, but not everyone does. The new variants keep appearing, and we get booster shots to fight them, but not everyone gets them, etc. And every year, 100,000 people die in the United States of COVID or COVID variants. That's a possible future. It's not a good one. I don't love it, but it's possible. And in that future, some people will continue to wear masks, socially distance. Other people will not. It'll be like almost what we have now, but a little bit better. That's what a very logical thing could be. We could get our act together, get everyone vaccinated, and like everyone in the world, it's not enough because the countries are semi-permeable membranes, so are completely permeable membranes. So getting one country vaccinated is not enough. If you get the world vaccinated, you can imagine stamping it out, right? We have stamped out other diseases, smallpox and things like that, by getting really good vaccines. If there aren't enough new people to be infected, the virus will die out. I just don't, right now, as I'm saying this, I'm not at all sure that we have the willpower to do that. And a lot of people just don't want to get vaccinated at all. So I'm not sure that's that happy scenario is going to come true. There's also much worse scenarios, right? I mean, like you say, there are other variants. In some sense, we were really, really lucky, believe it or not, with the coronavirus that it wasn't much more deadly. The tricky thing about the coronavirus was that it has a long incubation period, relatively speaking. You can have it and be contagious but not be symptomatic, which is half of the ingredients for a truly world-threatening viral plague, okay? The other half is everyone who gets it dies. If that were true, like if the worst possible virus would be one where everyone gets it, so it's super duper transmissible, okay? It's very, very contagious. And when you get it, you get no symptoms for a month or for 6 months. And then 6 months after you get it, you die with 100% probability, right? That kind of virus, if it were to exist, would wipe out humanity on Earth. It's probably not going to be that bad. Don't get too frightened by it. It's unlikely that some variant of the coronavirus is going to be 100% fatal. And we're pretty good at developing vaccines now, so we can protect against it. But some version of that is possible. So if the median is, it's kind of like the flu, but worse, the high-level hopeful future is we stamp it out, then the terrible apocalyptic future is there's a variant of it which is much, much more deadly and kills millions and millions and millions of people. I think all of these are on the table, and the longer we go without wiping it out, the more chance there is to develop into a much more virulent, deadly variant. I will say again, I am not an expert in this, so let that be provocation for your own thoughts, but listen to the real experts if you actually want to know what's going to happen. I just haven't talked to one recently about this exact question, so I'm just spitballing, not giving you expert knowledge here. Eugene Ilofsky says, were you a math prodigy who turned to physics or a physics prodigy who could do the necessary math? So I will demur on the question of whether I was a prodigy at all, but I did fall in love with physics very early, and it was physics that I fell in love with. And, not every decision you make when you're 10 years old turns out to be the right one, but for me, that was the right one. I've learned a lot of math subsequently, but math is not my passion. Like, if it doesn't help me understand the world, I get kind of tired of it pretty quickly. Like, you can follow Steven Strogatz, former Mindscape guest, on Twitter, and he's great. He's just a great Twitter follow, very good at explaining things and very entertaining and so forth. But man, he loves these little math puzzles. And I just look at him like, I don't care. It just doesn't do it for me. Like, what am I helping to understand by thinking about this? I can't think of anything. So and it's good that we're different in that way. It's good that there are both physicists and mathematicians. But for me, physics, easy call. Charlie H. says, I really admire the way you have great discussions with experts from all fields on Mindscape. What, if anything, have you found to be a key or significant difference between the Mindscape of science-y guests from that of humanistic-y guests? That's a good question. And to be honest, I have never thought about it. I've never really sort of looked for commonalities between those two groups. So there might be ones that I haven't thought of. So I'm not going to give you a very comprehensive, reliable answer here. And in fact, as you might have noticed, I have noticed, I'm constantly in the situation of interviewing someone who is not a physicist and them telling me, oh yeah, I was a physics major as an undergraduate or something like that. So even the humanistic people who I interview sometimes have like secret physics sympathies. So there's a huge selection effect in who I am picking, right? But also there's a selection effect in which scientists I'm picking, because I tend to pick scientists who have broader interests, interdisciplinary interests, etc. So I don't see a huge difference between them, but I'm picking humanists who tend to be science friendly, and also scientists who tend to be humanities friendly. So maybe it's not such a big surprise there. I mean, obviously there's like trivial differences. Scientists are more likely to want to write down equations or do experiments than humanists are. But I think that the general mindset is more or less similar. Christopher said, you once said on Joe Rogan's podcast that you think cities are good for the planet. Could you expand on that at all? Yeah, but mostly I would point you to an earlier podcast I did with Joe Walston on urbanization and the environment. And he's the one who convinced me of this. I've heard rumbles about it before, but Joe Walston is a conservationist by trade. So he's literally invested in conserving the environment. And he gives the world's best sales pitch for cities. Because look, given a certain number of people and a certain amount of economic activity, there's roughly speaking two extremes. One is you spread those people and that activity uniformly across the land, and you sort of despoil all of the land because there's people everywhere, or you concentrate those people and that activity in a small number of locations, and you leave the rest of the land for the planet and the environment and the ecology. Guess which one is better? And those concentrations of people and activity are called cities. That's what they are. At a very basic way, very basic level, You need fewer natural resources to live in a city than you do in the country. You don't drive as far. It's much like, look where I am right now in this apartment building in Boston, right downtown. There are other apartment units on most sides of my building. So guess what? If I heat it or cool it, I'm not then ejecting that heat differential right into the environment. I'm sharing it with other human beings right next to me. So it costs less. It's much better for the environment in terms of resources, etc., if human beings limit the fraction of the Earth's surface that they take over, roughly speaking. That's the point. Anonymous says, what would happen if you put one end of an arbitrarily strong and arbitrarily long cord into one black hole and the other end into another black hole? Would the black holes be pulled together? So, a couple quick thoughts here. One is, especially in relativity, but even more generally in physics, as soon as you say words like, or phrases like, arbitrarily strong and arbitrarily long, you're going to get into trouble. Arbitrarily long, okay, but arbitrarily strong chords are not really physical, right? Roughly speaking, and again, there's details here that I'm not going to get into, but roughly speaking, the stronger or more rigid a rod or a cord is, the faster sound travels down it. And you don't want your sound speed in your cord to be faster than the speed of light. You want it when you tug at one end, nothing happens to the other end until the speed of light has passed, or until a signal moving at the speed of light could get there. So it's a little bit unphysical to imagine these things, but I get what you mean. The reason why it's a hard question to answer is that if you have the black holes and there's nothing else in the universe, then even without the cord, they're going to be pulled together. They have gravity, right? The gravity will pull them together. So I believe, I'm not 100% certain about this, but I believe adding the cord in there will pull them together a little bit faster, because roughly speaking, they're pulling on the cord as well as the other black hole. But it's not a qualitative difference in the behavior. Okay, I'm going to group two questions together. Brent Meeker says, in Mindscape 63 on finding gravity within quantum mechanics, you speculated that there are only finitely many degrees of freedom in a given volume of space. Wouldn't this imply that there are also only finite many possible states, and so there will be a smallest non-zero probability of any possible event? Andrew K. says, due to Bekenstein's bound, in a finite volume of space, there can only be a finite number of bits of information. However, in quantum mechanics, real numbers are used all over the place. Is it worthwhile to try to replace these real numbers with rational numbers in order to only require a finite number of bits to represent them? So both of these questions are getting at the following idea, that the entropy of a black hole, let's put it this way, there's different ways of stating the same answer, but the entropy of a black hole, as Bekenstein and Hawking taught us, is a finite number. Whereas the entanglement entropy of a region of space in quantum field theory, remember we talked about entanglement entropy, and if I just take a region of space and think of the quantum fields inside that region, they are automatically entangled with quantum fields outside that region. That entropy, they have an entropy, the quantum fields inside a region have an entropy because of entanglement, and if you naively calculated it, you get infinity. And that's because there's an infinite number of ways to arrange what's happening in a region of space, because quantum field theory has an infinite number of degrees of freedom. So the fact that black holes have a finite entropy, and yet we think that black holes are maximum entropy for a given volume. I said before that black holes are not maximum entropy, but they are maximum entropy fixed volume, okay? And if you don't fix the volume, then you can always expand the entropy by expanding the volume of space. But for a fixed volume, black holes are the highest entropy you can get, and it's not infinite. That seems to indicate that quantum field theory is wrong, and that there is some finite dimensional quantum mechanical system that describes what goes on inside the black hole. That's not 100% accurate, because it's a sloppy kind of reasoning, but it's very plausible, and I suspect it's right. I suspect it's on the right track. But let me distinguish between two things. I think both questions are mixing up two different possibilities. There's the number of degrees of freedom in the sense of the number of dimensions of Hilbert space, the number of specific different directions in which your quantum state can point, okay? If I have a single spinning particle, a single electron, its spin is described by a two-dimensional Hilbert space, spin up or spin down. The cat in Schrodinger's cat also two-dimensional Hilbert space, awake or asleep. Obviously, there's many more degrees of freedom in the cat, but we're ignoring them, okay? If I have two particles that are spinning, I have 4 dimensions of Hilbert space. 2 times 2 is 4. If I have n particles, it's 2 to the n dimensions. But, so that's a finite dimensional Hilbert space. If that system of a finite number of spins were entangled, it would have a finite entropy, okay? Not an infinite entropy. But that's very different than the fact that each individual spin has a wave function that is a superposition of spin up and spin down, and the amplitudes of that superposition are continuous. They are not discrete, okay? That's not the idea that there's only a discrete set of probabilities that you could have for spin up or spin down is not part of quantum mechanics, not part of anyone's version of quantum mechanics. You could try to invent one, people have tried, but whatever you're doing is you're not doing what quantum mechanics says. So the finitude of either entanglement entropy in general or of the black hole entropy is the number of degrees of freedom, but it's not a discreteness of the wave function. It's just that the wave function is a function of a finite number of variables instead of an infinite number of variables. But the values that it can take on each one of those variables are still continuous, not discrete. I hope that's clear. It's a little bit more technical than I usually get here, but given the questions that were being asked, I hope that you can understand. Okay. Jim Murphy asks a priority question. I'm basically wondering whether the order of moments in time is necessarily fundamental. Could all moments of time exist independently without reference to moments before and after? I imagine the universe existing as a mathematical set of possible states, and time emerges from the fact that some states contain references to other states. For example, my brain right now contains memories of a brain a few seconds ago. This seems similar to your explanation for our perception of the flow of time, but your explanation still assumes a block universe rather than a collection of unconnected moments. So honestly, I'm just not sure what it would mean for the order of moments in time to not be fundamental. Especially if there are an infinite number of them, a smooth continuum of them, which I think that there probably are, but we don't know for sure, so I'm going to leave that aside. Let me say things that I think are true, and hopefully they will address your concerns rather than trying to guess what your concern is. We live in a universe that has 2 features that have to do with time. One is continuity. So what we mean by that is there are equations that tell us, whether it's Newton or Maxwell or Einstein or whatever, but given what the universe is doing at one moment of time, the way the laws of physics work is that they tell you what will happen at exactly the next moment. They are differential equations in time in particular, okay? So they describe a smooth evolution of the state of the universe from one moment to another. So in that sense, you could rearrange or ignore the ordering of the moments, but that would be dumb. that would be very bad strategically, because then it's hard to say what the laws of physics are even telling you, right? The laws of physics, as we know them, relate moments of time in a very specific order. Okay, that's one fact. The other fact is, like you say, the arrow of time. And it's a little bit tricky, subtle, the relationship here, because of determinism and reversibility. If you're Laplace's demon, if you know the microstates, then the entire future and past are, let's say that you're an Everettian about quantum mechanics too, so there's no fundamental indeterminism in quantum mechanics. The entire future and past are implicit in every moment to Laplace's demon, okay? So in that sense, Laplace's demon has perfect memories and perfect predictions. At the macroscopic level, for we emergent non-Laplace's demons, we have memories of the past and not of the future. That's an asymmetry that shows up, okay? So when you say, my brain right now contains memories of a brain a few seconds ago, that's a time-directed statement. Your brain right now does not contain memories of a few seconds from now. And the reason why that asymmetry exists is because entropy is increasing, okay? So that is, what I want to say about this is it's not fundamental. That fact that your brain, quote unquote, contains memories of a brain of a few seconds ago is a statement at the emergent approximate macroscopic level. At the microscopic level, your brain right now contains exact, or at least some broad swath of the universe, maybe a few light minutes across, centered on your brain, contains the information that determines both your brain a few seconds ago and your brain a few seconds in the future. So there's no directionality there at the microscopic level. So there's a temptation to think of something being contained in your brain that relates to the past but not the present, but that's only because we only have access to the macroscopic level. If we had micro information, we'd have equal information forward and backward. So what this has to do with moments of time existing independently without moments before and after, again, you're welcome to do that, but it seems to me to be a huge step backwards in convenience and understandability. The world is intelligible because we can predict what will happen at the next moment from what is happening right now. Mike Maloney says, you mentioned that the traditional scientific... Oh, am I grouping two questions together? I am grouping two questions together. Mike Maloney says, you mentioned that the traditional scientific method is not the way professional scientists actually do science. As a science teacher, I was wondering if you could think there is some other kind of method we could be teaching middle school and high school students that would better prepare them for careers in science. And Rasmus Kies Nierbeck says, in your opinion, what would be the most important thing to teach in schools regarding science in general or physics in particular that are now missing from the general curriculum? I do know that both teaching methods and curriculum is somewhat different in your country to mine, but still interested in your opinion from a physics professor's view. So I think that, Rasmus, you're probably looking for some thing like quantum mechanics or relativity or entropy or some physics concept. I do generally think that we are too reluctant to teach fun, modern, cool physics in high school and middle school. I think that we will teach Newton's laws, maybe a little bit of electricity and magnetism or something like that, but we're not going to teach general relativity. The equations are too scary. I don't see any reason why we shouldn't do at least a descriptive, non-equation-based explanation of these modern physics ideas, even in high school. But my real answer to your question is also the answer to the previous question, because what I would really want to teach kids in high school and in middle school is not the scientific method, but the real method by which science is done, not what we typically label the scientific method. For those of you who don't know, what is often labeled the scientific method in high school science courses is this fairly formalized procedure that goes back to Francis Bacon and his friends of doing science, whereby you propose a hypothesis, devise a test for your hypothesis, collect the data, determine whether your hypothesis passed the test, etc. It's vaguely related to what scientists actually do, but any real scientist knows that real science is way messier than that. And so I think the two things that I would like to get across to high school students about the real way science is done is, number one, that there is a procedure that is highly fallibilistic. It's not an algorithm for getting the truth. It's absolutely, science is basically a highly formalized version of trial and error. It's imagine many different possibilities, the hypotheses, and assign to them in a good Bayesian way. You don't need to necessarily use this language in high school students, but you could assign prior credences to them. Simpler theories would get higher credences. More complicated ones would get lower credences, but they would all get non-zero credence. And then you collect data, and they change your credences. But you could always be wrong. I mean, both your assignment of credences could be wrong, your calculation of likelihoods can be wrong, and most importantly, your data could be wrong. Like, have you ever done a laboratory experiment in high school and gotten the wrong answer? I have. I think most people probably have. That's an important part of doing science. It's not a collection of facts. It is a process, and it's a process that is highly fallibilistic. And the other aspect I would want to emphasize is that it's not even an orderly process. The scientific method we're taught, the Baconian scientific method, seems to, say you need to first write down your hypothesis, etc. No one really does that. It's a constant back and forth between observations, experiments, ideas. You're constantly spiraling or dialoguing, let's put it that way, between the real world and your thoughts about the real world. And that's okay. It's not, against the rules or anything like that. And I would like to explain that to high school students if I could. Okay. Mystery Horse says, given all of your success, I'm curious if you've abandoned ideas, papers, books, or other projects that you had invested a significant amount of energy into. If so, could you tell us about a particular failed idea that contributed to a successful future one? Yeah, I mean, that happens all the time, actually. And this is not, I mean, I think that I'm slower than many scientists in the sense that I will often get an idea and want to do it, and it'll take me a long time, years, before I actually do something about it. This happens all the time. This paper I wrote with Aidan Chatwin-Davies on the relationship between the second law of thermodynamics and the expansion of the universe. I had that idea years before. I was convinced that the second law and the cosmic no-hair theorem had to be related in some way. And it wasn't, I would occasionally tell my graduate students this, and they'd go, yeah, maybe. And Aidan was the one who was actually able to come up with a way of proving something, right? So it was never a failed idea, but it was a gestating one. My most highly cited paper is on what is now called F of R gravity. So it's a modification of general relativity that could possibly make the universe accelerate. I don't know if you want to call this a failure or not, but I came up with that idea because I was hopeful that it would explain both dark matter and dark energy, both rotation curves of galaxies and the acceleration of the universe. So it doesn't do that. It doesn't work for rotation curves of galaxies. So I figured that out. Like I said, oh yes, it could make the universe accelerate, but it will not explain rotation curves of galaxies. So in my mind, it was a failure. And so I didn't write it because it didn't do what I wanted to do. And it wasn't until my collaborators, Mark Trodden and others, independently came up with the idea and said, is this interesting? I'm like, well, I guess if everyone else is coming up with the same idea, maybe it is interesting. And we finally wrote the paper and it became a huge success. There you go. Other papers I had are very much like that. There's millions of ideas probably that I've had that have just failed and continue to fail, like have not grown into great papers, but I tend to just not remember them very well. So I'm not going to tell you any. Charlie Grover says, suppose one has a scalar field slowly rolling toward the minimum of its potential. A concrete example of this would be a quintessence field. It's commonly said excitations of a quintessence field have a mass, maybe around 10 to the minus 33 electron volts. What does it mean for excitations of a scalar field to have a specific mass while it is rolling? Clearly, okay, there's a longer question, but so what's going on is the following. Imagine you have a scalar field. So you're picturing in your head a potential, a hill, right? A landscape. And the scalar field is a dot that is rolling down that potential. And typically, most scalar fields, like the Higgs boson is a scalar field, pions are scalar fields, axions would be scalar fields if they existed. We haven't found any yet, but there you go. The mass of the scalar field is related to the curvature of the potential near its minimum, okay? Because if you think about it, so you have a minimum of a potential, so there's some value that the potential has, and then it has a first derivative, the slope, but the slope is always exactly zero because you're at the minimum. We told you you're at the minimum, so the slope of the potential is zero. The next interesting thing is the curvature, the second derivative of the potential. And that is basically telling you how much energy it costs to nudge the scalar field a little bit away from the minimum of its potential. And that energy cost shows up in particle physics language as the mass of the particle that you're looking at. So the relationship between the mass of a particle and the potential of the field that defines that particle is the mass is given by the second derivative, or really the square root of the second derivative of the potential near its minimum. Now, for a quintessence field, quintessence is a candidate for dark energy that is a slowly rolling scalar field. And by slow, we mean it takes longer than the current age of the universe to roll down its potential. And what that means is, unlike the Higgs or the axion or the pion, this field is not sitting at the bottom of its potential. So it has a bottom of the potential. It's just not there yet. It hasn't gotten there yet. It takes longer in the age of the universe to get there. So you're completely correct, Charlie, when we say that we will often talk about the mass of the quintessence field as if it were sitting there at the bottom of its potential and calculating the second derivative. That's cheating. We shouldn't really do that. When it's somewhere else on the potential, what you should do is expand, calculate the second derivative there, wherever it is, okay? Not at the minimum. And if it is at the minimum, then the value of the second derivative somewhere else is just not an interesting quantity. But if it's rolling slowly and hasn't gotten to the minimum yet, then the value of the second derivative where it is acts as the mass. It acts as the mass in the equations of motion for the scalar field. However, the reason why no one really makes a big deal about this is for a typical choice of potential, for a choice of potential that you haven't finely tuned in some way, it will more often than not be the case that the order of magnitude of the second derivative is the same wherever the field is as it will be once it gets to the minimum. That there's obvious counterexample to this, which is a field that just rolls off forever, okay, that doesn't even have a minimum. But for a typical field that is just generically rolling, the magnitude of the second derivative has a value that is comparable, same order of magnitude. So therefore, talking about the mass is sort of a proxy, sort of a quick and dirty way of getting at how strongly the potential is changing as the field value changes. That's all. So it's just sloppiness. I hate to give you a long answer. The short answer is we're just being sloppy. Sorry about that. Okay, we're nearing the end, folks. We have 2 more questions left. James Nancaro says, if there are many bubble universes, as in eternal inflation, and our universe is one of those, and the bubble universes are of various random sizes and larger universes are less likely than smaller ones, does this provide a solution to the Fermi paradox, why we don't see alien civilizations or their probes in our neighborhood? I don't think so. No, I mean, I get the idea that, if you have many, many different bubble universes, the probability of getting even one civilization per universe can be very small, and yet you're going to get a lot of civilizations because there's a lot of bubble universes, right? So in that scenario, you would, as I think, James, you're getting at, you would predict that each civilization is alone in its region of space. But the point is, you don't really need the multiverse for that. So, I mean, I think that logic is completely good and might even be correct, but you don't need the features of eternal inflation or bubble universes where like the laws of physics are different or anything like that. You could just imagine that our universe is really, really big and the probability of life forming and intelligent civilizations forming is very, very small. And then you explain the Fermi paradox, right? So you need that in your scenario. I'm calling it your scenario, but you need other things in your scenario, all these bubble universes. In my scenario, you just say the probability of life for intelligent civilizations is very small. That's it. Now we're here, right? So you might want to say, well, if the probability of life is very small, maybe the probability of us being here is very small. But this is, again, a longer, more nuanced discussion, but I think you should just conditionalize on us being here. We already know we're here. This is what Bayesians call old evidence. We shouldn't count it again. There's no theory we should be paying attention to that predicts we're not here, right? We've already taken into account the fact that we're here whenever we do any of this reasoning about anything. So our existence, I would argue, counts for strictly nothing when we're talking about the different probabilities of different theories of the universe. So as long as the probability of life forming is small, then forgetting about us, the question we're asking is, what is the probability of life or technologically advanced life forming somewhere else? And the answer will be small if the original number is sufficiently tiny. Okay, the last question, another bit of a curveball here. Gabor Peter Serre says, looking at the failure in Afghanistan, what do you think would be an effective way how Western democracies could help countries with strong influence of religious extremists if the goal is building a society where human rights are respected more? Would strengthening secular education in favor of religious education help? So again, to people a century from now, listening to the old Mindscape archives, we just had the American withdrawal from Afghanistan, not quite 2 decades, but close to 2 decades after we invaded there, after the September 11th attacks. And, tensions are running high right now. I don't want to step on anyone's toes. On the one hand, you have a bunch of people who say, look, we get into these wars to try to fix a whole country. And there's no end game, right? There's no surrender or anything like that we're looking for. The goal is nominally to transform a nation. But that's really hard. So we end up just staying there and people keep dying and nothing really good happens. There are other people, and so therefore we should leave, is their argument. And the other people say, look, there are really bad things happening in the world, human rights violations, dictatorships, atrocities of various forms, nurturing terrorists that can attack other countries, etc. And we, as the superpower, have an obligation, this side says, to go in there and stop that from happening. And as John McCain famously said when he was running for president, he would be willing to stay there for thousands of years if that's what it took to like tamp down the violence and the extremism in those countries. So there's one school of thought that says we shouldn't go in at all, and another one that says we should stay for thousands of years. And we recently were there for 20 years and we left, or 17 or 19 years or whatever it was. And it's been kind of a mess, to be very polite about it. You know, again, people disagree and tempers run high, but it's been a mess. Let's just put it that way. The withdrawal has been a mess. And so again, one side says, well, yeah, it was going to be a mess. There's nothing you could do. Like it was you had your finger in the dike and you're saying, what's going to happen if I remove my finger? Well, there's going to be a flood. There's just nothing else you can do about it. And the other side says there are ways to withdraw that would have been much better, that would have been not nearly as messy, okay? I'm not going to get into that one either. The question that Gabor is asking is, if you imagine that we go there, if you imagine that we invade a country, and, you know, okay, we have the military capabilities of removing its government from power, putting another government into power, stopping terrorist activity, or at least fighting against it, et cetera. Those things we can do. But what about the fabric of the country? Like, what about the fact that there are people in this country, and I'm not even specializing to Afghanistan. I'm trying to be more general than that. So the specifics of Afghanistan are, again, not something I'm an expert in. None of this is stuff I'm an expert in. But it's my AMA, and I'm at the end of it, so I'm going to pontificate. There are people in this country, this hypothetical country, who support the bad guys, right? I mean, otherwise they wouldn't have gotten into power in the first place. So how do you not just overthrow the government, but change the fabric of the society and the culture so that the set of people who support the bad guys is sufficiently small and powerless that we don't need to be there to hold them down? That's the question that is being asked. And the short answer is, I don't know. Even at this sort of very loosey-goosey end of the AMA podcast episode, letting our hair down kind of mode, I just have such enormous respect for the difficulty of this question that I think it would do a disservice to be too glib about it. How do you change the fabric of a country? Just an hour ago, I said it's hard to change the fabric of a single person you're in a relationship with. Changing the fabric of a country is really hard to imagine doing. Having said that, I will say just one little tiny thing, which is that what we tend to do historically is mostly military, right? That's where we focus our efforts, we being the United States in the last century of its history. We invade and we, keep track of military actions by the bad guys and we try to prevent them, et cetera, et cetera. We're much less good at creating a stable, functioning society in the non-military aspects of the country. I'm not even sure that we try very hard. We try a little bit, but the idea of better schools, better education, better healthcare, ideas that, by the way, would be also nice to have in our own country, but these ideas are just not emphasized in these adventures very often. So on the one hand, could we have more success in these adventures if we did more of that? Maybe. I honestly don't know. But it wouldn't hurt to try. I think that there's enough historical evidence that we're not able to change countries that don't want to be changed. But what we can do, again, just like the question with China earlier, the thing that we have in our power to do is to be a good example, to, not just say, be like us, to hector the other countries and say, like, you should be like us, but to make them want to be like us by being awesome, by having great human rights, by being economically vibrant, by protecting our own people, the poor people, the less well off, and by giving them the way to do that, right? If we had somehow, and I don't think it's possible, so I'm not casting aspersions here, but if we could have converted Afghanistan into a prosperous functioning democracy, we would not be in this mess, right? Now, that's much more easily said than done. So again, I'm not saying that we should have just done it, snapping our fingers, but it should be the goal. It should be like the aspiration when we go into these. And if we can't, then we shouldn't linger there very, very long. I do think the final thought here is that, truth in history. I was very much against the invasion of Iraq when George W. Bush was president, but I was in favor of the invasion of Afghanistan on the thought that the terrorists who were based in Afghanistan had just done a terrible terrorist attack against us, and we should punish them somehow. But I would have been much, much more in favor of something very quick in and out, rather than an attempt to go there and rebuild the country. Go in and go out, and by all means, give them aid and give them resources to improve their country and things like that. We should be doing those things anyway, even to other countries that do not harbor terrorists that attack us. So certainly we should be doing it if we want to win the hearts and minds of countries where we don't want them to support the bad guys. But look, I'm an idealist at heart, an optimist at heart. I think that there are ways that society can be much better, both other societies and our own. I don't think that religion is the fundamental issue here, but it's an issue. It's part of the story. And if you want to say that my picture of what we should do in these other countries is hopelessly naive and it will never work, and you want to characterize your own point of view as more realistic and hard-nosed, very well. You might very well be right. I'm not an expert on this. I'm just an aspirationalist who thinks that we should, I'm becoming more of a deontologist, honestly, in my old age. I'm thinking that rather than inventing consequentialist rules for making the world a better place, we should worry about acting in the good ways ourselves, and maybe the world will follow us. There you go. Thanks for paying attention. Thanks for doing this AMA. See you next month. And thanks very much for supporting the Mindscape podcast. I don't say it enough, but it is tremendously warming to my heart that as many people as do join Patreon and throw in a few pennies here and there to support this little endeavor that we all do together. Thanks. Bye-bye.